Yeah, so at the beginning, I would like to welcome you officially now, all of you, dear ladies and gentlemen. I'm happy to have such a great audience for our consortium. It's a great pleasure for us that you take your time for us and that we get the chance to present some results, not only out of our project, but also external people. At first, let me briefly introduce myself. My name is Tobias Wille. I'm working at DLR since 2005, and last more than 8 years, I'm here at the Institute of Composite Structures and Adaptive Systems, leading Department of Structural Mechanics. So the whole institute itself is, as the name says, dealing with composite structures from all kinds of perspectives throughout the whole development chain, from material development down to a demonstration phase and testing. And my personal background is on developing structural mechanical analysis methods and test methods. And yeah, 5 years ago, roughly, I've been had the pleasure really to develop the concept for this SuCoHS project together with the participants, with the whole consortium. This was in the beginning a lot of interviews, talking to industrial end users and to suppliers what their needs are to fulfill really a technology roadmap and what particular objectives do we need to develop. And then all of us have been sitting together in several hours and days and developing such a concepts and methodology, writing a full proposal. And we have been very lucky that it got accepted with actually great marks by then. And now, 5 years later, we are not at the beginning of this project, we are at the end of this project, which is a 3.5 years running project due to a half-year extension, originally planned for 3 years in total. And I can say that I'm happy to have all people here on board. And to begin with, I would like to show a few slides for welcoming. Sorry, I have troubles now switching the slides. Right, and in order to give you more information about SuCoHS, at first briefly explaining what the name SuCoHS stands for, since it's not so easy to read. So what we are aiming at is sustainable and cost-efficient composite structures, which are demanding high temperature and fire resistance. So we do see issues not only for classical mechanical aspects, but especially looking into areas which are not so comfortable for classical composites. How can we increase the exploitation by going or by allowing higher temperatures? How can we improve materials that can withstand higher temperatures or fire conditions? And because that's such a broad objective, we have been coming up with a consortium which is also quite large. As you can see here on the slide, we are 14 partners, which means roughly 40 engineers and researchers sitting together in these different disciplines, spread all over Europe in 7 countries, and even quite evenly distributed. And that was really a great time we have had. Any success stories we can present you hopefully today and come in discussion with you. And what is the aim of today's workshop? What we'd like to do is to have a second loop for a public workshop. We have already had one last year presenting intermediate results. Now, since this project is ending, we'd like to give you an overview of all final results from first material developments down to final demonstration of a pilot demonstrator, which have been manufactured and tested. And now, especially what we do not want only, we just don't want to see it as a one-way presentation. We really like to get in contact with you. So that means that we'd like to get your feedback directly through chat, through the Slido systems, which will get explained to you in a few minutes. So please get involved here in the today and in tomorrow's discussion. This is what we are aiming for, to get your feedback, as you are a stakeholder from different perspectives. If you are an OEM and end user, or if you are a supplier, even an SME, or even people from research organizations, please give us your feedback here today. It's a great chance. Also, I think also something special to have colleagues from the authorities in the group, so that we can really look beyond technical perspectives, even into realization aspects. And I hope that we can derive together also further needs, further means that are to be tackled beyond this project. At this point, I would like to introduce you also Vladimir Sipurier, who is the commissioner, has supported us throughout the last years, always available for feedback. And so Vladimir Sipurier, I think you would like to have a few words your own at the beginning here, after I will present this agenda of today's meeting. So after a first welcome, we also like to introduce Bastian Brenken from Composites United. I will have a few words. Then Dominika Behrendt from LAB will explain how to use our chat and Slido systems for getting you involved. And then we go into technical details. I will give you more details about the SuCoHS project in an overall presentation. And after that, we will have three very interesting detailed discussions about the industrial demonstrators, which are led by Spirit Aerosystems, Annova, and Collins Aerospace. And then there will be a coffee break in the afternoon before we then go into a panel discussion, which will be led by Professor Wiedemann, and where we have authority people on board to support us in our discussion. This is today's agenda. Maybe I'd like to ask for questions at this point. Are there any questions already? If that's not the case, then I would like to welcome you, Vladimir. If you can take over a few words and spend a few words for us.
Sure, of course. Thank you very much, Tobias, and good afternoon, ladies and gentlemen. So indeed, my name is Vladimir Sipurier, and I'm a project officer at CINEA, which is the European Climate Infrastructure and Environment Executive Agency of the European Commission. Basically, we have the delegation of managing Horizon 2020 programs in transport and also now in Horizon Europe. So it was my pleasure to be the project officer of SuCoHS during the Grand Agreement preparation and also throughout the lifetime of the project. SuCoHS was founded from a topic calling for maintaining the industrial leadership in aeronautics in Europe. And I believe that throughout these 3 years and a half that the project has been working on high resistance composite materials, as Tobias has already explained, has certainly contributed to maintain and increase this industrial leadership in aeronautics throughout Europe. From my side, I will not take much more time because the real content comes after me, but I would just want to thank you all the partners in the consortium SuCoHS for the work done until basically today, which is this is the last month of the project, and also to the participants, more than 80 participants already connected. And I wish you very fruitful discussions. I hope that you will find very interesting results of the project, and I wish you a good follow-up, not only today but also tomorrow throughout the presentations of the partners. So that's all from my side. Thank you very much once again, and I hand over to the next speaker.
Thank you very much, Vladimir. Nice to have you here. So yes, the next speaker will be Bastian Brenken from Composites United. He's the manager director of Composites United North. So please, Bastian, the stage is yours to have a few words for us here as we are organizing this also together.
Yeah, Tobias, thank you very much for the kind introduction, and also welcome everyone on behalf of me and of course on behalf of Composites United. We supported the project team by advertising this event. I think this very interesting and important event in our network, and we gladly did that because I think it's really essential to get advancements and to have progress in the field of fire and temperature resistance. We see as Composites United that fire safety oftentimes really still is a showstopper for composites for a broader use, and not only in aerospace but in many other industries like shipbuilding, like construction as well. So it's really, I think, a great project. I think we will see some exciting outcomes today and tomorrow, and I really do look forward to the event. In addition to welcoming you, I would like to take the opportunity to briefly introduce you to Composites United. So I'll try to share only a few slides to show you. So I hope you can see my screen.
You can.
So I will run through quickly to not keep you waiting for the content too long. Composites United is a leading network for fiber reinforced high performance materials worldwide. We have a regional structure in Germany. Tobias already mentioned I'm responsible for this northern part here, but also clusters in Switzerland and Austria, and we have representatives in Asia, mainly in Japan, China, Korea, and India. We have, in addition to these regional clusters, we have specialist networks, CU Bau, CU Construction, and CU Ceramic Composites. So they are also temperature and fire resistance is playing a crucial role for these colleagues of mine. And at the moment, we have about 370 members, mainly SME. What are our activities? Well, in the center is the network. We connect composite people along the whole value chain, from education all the way to recycling and reuse of the material. We have different formats. Innovation days are one-day conferences. Web seminars are webinars we have every Wednesday for our members to present themselves. And then we support technology and innovations by helping to set up projects. We create market access for our members through our 2 international clusters and the representatives in Asia. We have a broad knowledge base and provide education and market information. And of course, the daily communication, newsletters, print media, etc. is very important. An essential part of the networks are working groups, and I put this specialized slide in here because we also founded the working group Fire Safety mid last year, and we already had 3 meetings that took place. So it's a very, very important topic in our network of very high interest, and we have players from different industries coming together there. Dr. Hauke Lengsfeld, the leader of this working group, will be part in the discussion tomorrow at the end of the day together with Tobias. And working groups are basically pre-competitive exchange of information. You can see the development of others, discuss technical issues and challenges, and have a professional social networking. We have now several were founded still last year, but more than 45 working groups covering basically all topics related to composites, from recycling, reuse, education, industry 4.0, etc., etc. And typically 1 to 4 meetings per group per year. So this is a very essential part of our network. Communication, the web seminar Wednesday I mentioned already. On this slide, I want to highlight the LightCon, it's the Lightweight Convention. It's a new international convention for lightweight solutions we organized together with the Deutsche Messe AG, the organizer of the Hannover Messe. Some of you may know the Hannover Messe as largest industrial fair in the world. And we will have the premiere of the LightCon on the 1st and 2nd June this year, actually in parallel with the Hannover Messe this year. So if you're in Hannover for the Hannover Messe, come and visit Hall 19 and come and check out the LightCon. Yeah, and then you see other means of communication in our network. We are very active in the social networks and support our members there, especially on LinkedIn. But also the traditional communication is really important still to our members, like the CU reports. You see our printed magazine that we publish twice a year. And lastly, I want to highlight that we are indeed an international network. It's not only Europe, not only Germany. We have members in the US and Asia, but mainly in Europe. And we are also still very active even in these pandemic times. When you typically visited Japan or the United States, we do virtual events like this one together with our international partners here. Some 2 examples of last year. That's basically my brief introduction. Thank you very much. With that, I thank you for the time, for the opportunity to present Composites United, and hand the words back to Dominika.
Great, Dominika. So then you can explain our system for today.
Perfect. Okay, so I'm taking over.
Yeah, while Dominika is opening the slides, I'd like to introduce you a little bit more. So Dominika Behrendt is working for the company LUP since the last 11 years. And as far as I know, she's now already involved in about 15 proposals for European projects, which she is supporting as a European project manager, as a consultant. And which is remarkable is that I think you have been not only involved in 15 proposals, but 11 projects, which is a remarkable success rate for proposal funding. So this is great. And I can say that you've been really a great support within this project. So today and tomorrow we will only talk about technical developments, but in fact the management behind is even as important as well. So please support us now with the system.
Thank you very much, Tobias, for the introduction. So yes, hello everyone. My name is Dominika Behrendt, and so I've been working for LUP for more than 10 years, as Tobias said. And we are one of the partners of the project, and we are supporting the consortium in project management and communication and dissemination activities. So that's why probably most of you have been in contact with me regarding the registration for this event. So yeah, thank you for the introduction. And before we get to the heart of the matter, we would like to go through some best practices for the use of WebEx and Slido to make sure that the participation is smooth for everyone. And regarding the speaking during the event, as you probably saw at the beginning, all the participants were muted by the organizer. So once the chair or the moderator of the session gives you the floor, please don't forget to unmute your microphone and to speak in a slow and clear manner. Please be proactive by minimizing the sources of background noise in your workspace. So probably try to close your window or the door to your office so that we don't hear your colleagues talking. So please think about these little details. When you are not speaking, place yourself on mute, and otherwise the organizer will place you on mute. So keep in mind every time that if you want to speak, you have to unmute your microphone, because I can mute you, but I cannot unmute you. So you have to think about that. Given that this is a fully virtual event, and given that we have a lot of participants, we propose to use the Slido application to ask the questions, manage the questions and answers during the event. So you can see normally the Slido application in the right sidebar of your WebEx meeting interface. So it should be here. And we will be using the feature Q&A that is visible here, and it will be live. So it means that all the questions that will be posted by the participants will be immediately seen and visible for all the participants. So if your IT settings are okay, your Slido normally should be active, and you should be able to see this message. And if your IT settings are not set to allow Slido to show during your WebEx meeting, you can use the feature chat of WebEx to ask your questions. So this should be visible here at the bottom right side of your WebEx meeting interface. So don't hesitate. Every time you want to ask a question, just type your question either in Slido or in the WebEx chat, so that we can have an overview of all the questions that are being asked by the participants. And if you are using Slido or the WebEx chat, please, whenever this is possible, type the name of the person to whom you address the question. This will be easier for the chair of the meeting and for the moderators to manage the questions and ask the right people to answer. And what is also interesting with Slido is that you can vote for the questions that you find interesting, so that they are moved to the top of the list. And they will have a greater chance to be addressed during the discussion time, because as you know, we have a limited discussion time, and if there are a lot of questions, there may be not enough time to answer all of them. So if you vote for the questions, we will prioritize them at the top of the list, and we will answer them live during the event. And for all the others for which we will not have enough time to answer, they will be answered in writing and provided after the event. And so normally in a few days, we will provide, publish on the SuCoHS website, the dissemination material dedicated to this final public workshop. So it will contain the recording of the 2 days of the event. So for your information, the whole workshop today and tomorrow will be recorded. So the session today is already being recorded for your information. We will also provide in this dissemination material the public versions of the presentations and the questions and answers that will be addressed during the event, so they will be provided in writing. So this will be our dissemination module that will be dedicated to this final workshop, and it will be freely available to everyone on the project website. And so that would be all from my side. Do you have any questions, technical questions regarding the use of Slido or WebEx or any other comment? If not, I think we can continue, Tobias.
Okay. Well, thanks. We're pretty good in time at this point, so I hope I will be within time as well. And now, according to our agenda, I would take the next minutes in order to introduce you to the project in an overview. So that means I will give a few details. And I have to share the presentation, I can see now. Forgot to do that. A second, please. I hope it's working.
Yes, it is, Tobias.
Great. So just waiting for this slide to switch. Okay. So I'll give you a brief outline at first. I will explain a bit about our motivation behind. So what are the drivers? Why did we look into these aspects? Which particular project objectives did we define based on the industrial requirements? And how is the consortium set up according to have sufficient competences on board? And then especially I will go into some selected results throughout all work packages that have been worked with. Of course, I cannot present all results, but just a few selected ones. And please keep in mind that all of these will be very brief only, and you will get a chance later on within the afternoon to see more details, for instance, during the use case presentations, but also tomorrow, for instance, when we talk about individual technologies, we will have a lot of presentations on all of those. And then finally, I'd like to conclude and keep you updated. So at first, what is the motivation behind what brought us to that story? So you can see a few pictures here on the first slide where applications of fire and temperature applications have been looked at based on previous projects. For instance, when I look into a tail boom of a helicopter where we have hot gas impinging the tail boom, for instance, you will always have issues. How can I increase, for instance, engine power, but not increasing the maximum operating thermal impingement on the tail boom? Or other applications like within this project where we look into a tail cone of a structure where the MPU is located, we will see a lot about this. You can also see a nacelle application or a seat case of interior structure, which is of course, has to withstand a fire and crash scenario. So there are quite a few applications already in air, and in the future also applications, for instance, of integrated engines play a role where we look into lightweight constructions, and that automatically raises the question if we can increase the exploitation of lightweight composites in this area in order to substitute materials or even improve performance and also reduce cost or environmental impact. And here I told you that we do have these 3 use cases, which are going to be explained in detail later. As an overview, I can like to show you these pictures. At first, on the left-hand side, you can see the nacelle use case, which is an inner fixed structure inside the nacelle, which is currently a quite complex design made of multi-materials, different assembly steps, including insulation, blankets, etc. So quite costly part. With several subparts, and we have a service temperature of more than 300 degrees Celsius, which leads to the need for blankets, for instance, inside. On the second hand, the second use case is dealing with the rear end of the classical fuselage, where we do have the APU inside. And the question that is not new but not solved yet is how could we get rid of the APU housing, which is a titanium box that just gives additional weight to the structure, but not more. And therefore, the question was, can we get rid of it by having an alternative material and design of the surrounding airframe structure, which is, of course, has to ensure fire resistance and damage tolerance criteria as required by certification. At third, the use case of a composite interior shell is looked at as again, different one, having high fire requirements, FST requirements, not only flammability. And in this case, also the other question is, how can we reduce cost again? How can we improve performance also for the manufacturer in order to be leading manufacturer also here? Based on these three use cases, we will defining objectives, and we have seen that there are always an integral approach has to be followed. It's not sufficient to only look at materials or only look at manufacturing or design aspects. No, we do have to have the broad overview and see how everything comes together, and how we can really develop missing links, missing bricks in all of these situations. And that's what I mean is that we do have also potentials that we look into design aspects. So what kind of processes during design can we improve? Which aspects during manufacturing can we improve? And what are the additional impacts that we can use also for the operation phase? During design, you can see, I hope you can see, it's quite maybe a small picture. What shall be explained here is that there is a potential in terms of exploiting structural performance because of the current exploitation of materials, where we always use very conservative requirements, looking at the worst case scenarios in terms of temperature that may appear somewhere locally. And then this very local temperature hotspot is applied usually for the whole composite part. And what of course comes into mind is how can we go around, how can we consider local hotspots and avoid to use them as a classical global design criteria. So that means that we, in order to exploit this, we need to have a better phenomenological understanding about these thermal fields and thermomechanical interaction. We do have to have very reliable simulation tools in order to predict, and we might also have to have sensor systems which may be integrated into the structure later on in order to ensure that local hotspots are not exceeded, for instance, and to get that feedback also within maintenance strategies or later subsequent design steps. During manufacturing, we see high potentials by using automation, and you will see also a lot on this today. Automation, but also in combination with sensor systems, which are integrated into the manufacturing lines, no matter if it's the composite preforming or curing analysis, for instance, and steer your process based on this in order to achieve minimal waste or defects during manufacturing. And lately, once sensors have been integrated during the manufacturing, also some of those sensors still may remain within the structure, and you will have a double use, a continuous use during operation to actually monitor strains or temperatures during operation, and therefore have a potential for maintenance scheduling. So this is the overall objectives. And now I don't read all these aspects for you here, but we have had basically 5 technical work packages. Work package 1 on materials and manufacturing processes, work package 2 on analysis methods and allowables, work package 3 on sensor systems and evaluation of sensor data. And then we do have 2 work packages on testing and validation, as well as final pilot demonstration phase. And now within each of those work packages, there have been technical developments first on a material stage or material level and subcomponent level, and then they have been integrated in order to perform validation on higher TRL. Now, regarding the consortium, I have already told you that we have been a large consortium of 14 partners. Now I'll give you more details about this. For industrial end users, there is another Spirit Aerosystems and Collins Aerospace, having actually defining the roadmap for their use cases, the needs, and finally responsible also for the pilot demonstration and evaluation of results on that structural level. But they can't work on their own. That's why we need this European project and need funding, because now a lot of SME are involved in order to facilitate the developments. You have been introduced to LUP as a managing and coordination support, but then technology, we do have material developments, developments of sensor systems, databases, and that's where you can see that companies like NTPT, Synthesites, Transference Chemicals, Photon First, and formerly also Apodius are on board. Unfortunately, Hexagon Apodius has been only partner in the first 2 years, and then the company actually could not survive. So therefore, they had to step out of this project. And we will present a few results which have been developed until then. Now, regarding the fundamental research, we also had HONORAR and NLR besides CLR in order to perform material characterization and understanding of phenomenological behavior, and also to perform manufacturing trials and testing and manufacturing also of the demonstrators, as well as to perform testing wherever possible. And besides research organizations, we do also have universities which have been again developing materials and simulation methods when it comes to process simulation, or also supporting probabilistic analysis for the future. On the next slide, now it comes to detailed results. In brief, as I say, so I will not explain all the pictures. I will just give you some hints, and then you have the chance to discuss later on throughout this workshop. At the beginning of this project, we have been dealing a lot with material screening, selecting the baseline of our developments and the baseline for further developments of material modification, alternative materials, and to see which potentials to be used. For this, there is a public deliverable existing, which can be downloaded from the website, where you can see which material we have selected based on which decision, which criteria as well. And for us, we have been selecting according to our 3 use cases, but of course, there are other applications where you might have selected another material. At second, it's not only a matter of selecting materials and development. We also had discussed about which test setup do we need for which step within our development process. And for instance, also when it comes to a material screening at the beginning, we need to be efficient. We cannot use detailed test programs which drives us for years. We do have to have fast decisions. And that's why, for instance, there's also a development performed in terms of simplified testing here, by example, an efficient test procedure in order to determine heat release and or to perform a material characterization for fire properties, and based on a combination by a TGA and DSC measurement. Finally, for the selected materials, we have been dealing a lot with two different material types. At first, material cyanide ester was used and modified by University of North Switzerland. And we will have also a presentation for that particular developments tomorrow, given by Christian Brauner on one hand, and then there was a handover to NTPT, to Marika, to perform and to manufacture prepreg material, which is a thin ply material that can be used for our manufacturing also in AFP later on. And this material, the cyanide ester, was the main focus was how to modify the material so that it can comply with the industrial use case requirements in terms of toughness and temperature requirements, and manufacturability, of course. At second, we have been looking into a bio-based material from Transference Chemicals, furan-based materials. So also here, Hans Heudongs will give a presentation together with Matthias Kechtermans on that development. Also, this material has been starting on a certain baseline, and then further modification according to the use cases have been performed to meet, again, fire and mechanical requirements, so that this material can be used, for instance, for our seat structure. And again, to do this, there has been developing and testing from material level up to a fire test also in order to certify that material, or to do the steps towards the certification, I would say. Next, we've been looking into manufacturing technologies, and mostly at NLR here, the developments have been performed when we look into automated fiber placement You can see by those pictures that the complex geometries of those demonstrators makes it requires quite a lot of technical discussions and concept studies, how and where AFP can be used for which material. So what are the material requirements so that the material can be laid up in a really excellent deposition accuracy. So what are the potentials of fiber steering? What is the effect? How we can use thin ply material? How could we integrate also sensors? As you might see on the right bottom pictures, fiber gratings have been integrated. So there have been a strong developments in this field for all use cases. In the middle picture, you can see also local stiffeners in order to have stiffness where we need it from load perspectives, but having a real high weight savings here with that monolithic structure for the seat case. So all this will be explained, for instance, by the presentation by SuCoHS in the lab tour and also in his own presentation tomorrow, but additionally also within the use case presentations today. For process monitoring, you can see a picture here on the top, which is taken during our midterm review 2 years ago. And here, mainly by Enola and Hexagon, you can see a demonstration how the fiber placement monitoring system, which is an optical system by a camera with diffuse lighting, that was mounted onto the AFP head. And it was allowed to really have an in situ process monitoring that at full layup speed, the system was picking up the fiber courses. The fiber courses were automatically translated and mapped into our CAD model and the predictive fiber steering simulation. We had an in situ comparison of the deviations between prediction and actual layup, and it made it possible also to have an in situ evaluation from structural point of view if that deviation makes a difference or not. So unfortunately, since Hexagon had been, it's not existing anymore, and there's no, we cannot show you an update by now, but we have seen quite a lot of capabilities here. Additionally to the fiber deposition monitoring, we look into curing monitoring and also issues here from industrial point of view. Nikos Pantelidis will present you some results, how, for instance, these online cure measurement systems can be used also for carbon fiber without glass insulation, how a new technology of a cure simulator can be applied if you do not have capabilities to integrate cure monitoring systems inside the autoclave, for instance. So these are issues which have been developed and used within this project according to industrial needs. I told you that sensor systems like the FBGs, fiber break gratings, have been integrated into the structure during manufacturing by AFP. And here on the left-hand side, I'm not sure if you can see it really, but the small fiber break gratings are directly coming out of the structure. And those have been used for us in order to simulate a real operation. We have been simulating in our thermomechanical test facility. So the fiber breaks will be used, have been used for monitoring the actual thermal loading and mechanical loading, and therefore also helping us for validating our simulation methods. This presentation will be also given tomorrow by Gideon Langedank. Looking into analysis methods and allowables, we have been discussing about the phenomenological behavior of such a structure. For instance, heat impingement, if it hits a structure, is it only locally? How does it develop throughout the structure? What happens if a stringer still is cold, but the skin field is hot, for instance, and how could this be used, and that understanding in order to further exploit our design. And then it came along with material modeling in order to model stiffness, strength, and also degradation under fire. So there you will also see some presentations throughout the meetings, which material behavior does actually exist. So based on physical testing on the material level, where we have been tested also at higher temperatures, 250, 300 degrees Celsius, in order to have the full range of the material behavior captured, and then how to derive material models from this. Beyond a classical deterministic design, for instance, Technical University Hamburg and DLR have been looking into probabilistic analysis to use deterministic FEA, integrate them into thermomechanical coupled analysis, and then take this as a baseline for deriving surrogate models and perform probabilistic analysis to assess if that probabilistic analysis helps us maybe to challenge our allowables or to have an enhanced definition of allowables on a structure level. And also, which is quite fundamental, when we look into analysis methods, the question is how can analysis methods be used also to predict fire behavior and structural behavior under fire conditions. And you will also have a presentation given by Juan Pench on this fire simulation activity, which will be held tomorrow, where he's been showing how that can be used, how can this be applied, or what is the current status to do for the another use case. And beyond analysis, physical testing played an important role. So for instance, when we talk about fire analysis, we will give you also insights about the test pyramid, starting from very fundamental coupon level analysis, as I told you, regarding material screening, but then also into more details, coupon investigation, interesting test setups which are available at Onera, for instance, the so-called blade test facility, and also classical large coupon fire test, until we come up to a structural level fire test in order to certify or to at least qualify, prove the fire behavior, and afterwards mechanical performance after fire conditioning. And in parallel to fire testing, also thermomechanical coupled analysis by a thermix facility is performed. And also for that, we are offering you to attend a lab tour, virtually, of course, only. But Martin Liebisch will invite you also for a lab tour tomorrow to show you a physical test live. So here we are now at the end of this project. The initial sketches and CAD drawings are now supplemented by actual physical demonstrators. You can see a few pictures now, just keeping you awake and interested for the next presentations. So I can tell that it was really challenging, quite comprehensive developments. And I'm very also optimistic and looking forward to the next presentations where you can see much more details than just I have given you in a broad overview, and to look into the different technologies from material developments, manufacturing, analysis, and testing, up to final demonstration. Dominika has also mentioned that we are willing to stay in contact with you. So if you have not already been maybe part of the LinkedIn page, you are always invited to visit our website to download the public deliverables, download our newsletters. And also after this event, you will be able to download the presentations and videos that have been taken. So therefore, thank you very much for your attendance so far. And I can see that I am on time, which is good. Still 5 minutes left for first feedback questions, if you like. This is not the case. Then we may already introduce the next session. So the next session will be now dealing with the 3 use cases. And at first, I would like to welcome Daniel Green. Daniel Green from Spirit Aerosystems. Please let me briefly introduce Daniel to you. He has been now working at Spirit Aerosystems, formerly Bombardier, since May 2009. And here within the Department of Research and Technology on Materials and Process Engineering, he has been gaining expertise and great expertise now on composite development, not only on project management, but also on the details of resin infusion, automated fiber placement, topic of multifunctional materials, and particularly also sandwich materials, as well as material properties and testing procedures, as all of them always belong together. And such as also within our project, SuCoHS, he has been involved in several R&D projects, has been a lead engineer and in UK and European funded projects developing materials and manufacturing processes, etc. So now he's going to present you our use case of skewed arrow systems.
Thanks, Tobias. Can you hear me okay?
Oh, yes, great.
Great. Okay, so good afternoon, everyone. As Tobias introduced, my name is Daniel Breen. I work for Spirit Aerosystems in Belfast, Northern Ireland. And as part of the research and technology organisation here, I've been involved in several projects and with Spirit now for 13 years. So with that, I'll continue on and showcase my presentation. So this is about our composite inner fixed structure demonstrator use case. It's part of an nacelle application, which I'll take you through a bit of background to. It's a highly complex component in terms of its shape and the complexity of manufacturing it. So with that, I'll take you through the presentation. So just very briefly, just one slide giving a background on Spirit Aerosystems. So we're one of the largest manufacturers of aerostructures for commercial aircraft, business jets and defense applications. Headquartered in Wichita in Kansas in the United States. I believe we have around 15,000 employees today worldwide. With significant experience of both composite and advanced metallic manufacturing solutions. Core products include integrated wings, wing components, fuselages and nacelles. And in terms of the SuCoHS project, it's the Short Brothers site in Belfast, where I'm based in Northern Ireland, which is ex-Bombardier Aerostructures, which is acquired by Spirit in November 2020, who is the SuCoHS project partner. So just to give a general overview of what an inner fixed structure is. So if we look at the breakdown of an aircraft engine, the cell at the top right-hand image, it's made of an inlet cowl, a fan cowl, a thrust reverser unit and exhaust system. And the inner fixed structure is part of the thrust reverser unit, and as the name suggests, it is fixed, therefore no moving components, and it is structural. The inner fixed structure has considerable functionality, and I'll discuss that in the next slide. In the picture just on the left-hand side there, you can see the inner. It has as part of the assembly of a thrust reverser unit, and you can see it comprises of two halves, a left hand and a right hand. Since each half is manufactured separately and they're of equal complexity, our composite demo within the SuCoHS project focuses on one half only. So considerable functionality, as I mentioned. So aircraft engines, they produce significant vibration and are subjected to intense loads throughout flight. So including landing, whenever the thrust reverser is actually deployed, the key function of the inner fixed structure are structural integrity and fatigue resistance. The engine also produces, of course, tremendous amounts of heat. Therefore, the IFS, in short, I should probably use that term from now on, the IFS must not only be heat resistant, but also aid engine cooling by actively conducting heat from the hot side of the hot engine side to the cool bypass side. Noise attenuation is also a very important function of the IFS, since it is engineered with acoustic dampening in mind. And finally, the IFS segregates the engine core casing. You can see the engine in the left image there. So there's a complex network of pipework as well around the compressor area of the engine, and the IFS segregates this from the bypass side, and ultimately, you know, it requires aerodynamic properties for the inner bypass wall to ensure smooth airflow directing from the front of the engine to the rear. So in terms of the SuCoHS, our work package itself, what are their key objectives? So it was to develop the capability of manufacturing an automated fiber-placed composite inner fixed structure, which will satisfy a complex set of requirements, whilst providing the following benefits over the traditionally manufactured metallic IFS, which in Belfast is what we do. So the targets was reduce part count, improve fatigue resistance, improve noise attenuation, and potential weight savings and cost savings. I say potential, that the business case for that was not evaluated within this project, so I'm not going to get into, if there will be weight savings or cost savings. I'll maybe just point out that we do in Belfast, as I said, produce metallic interfix structures, and as a material base, the thermal conductivity of metals is of course going to be over and above that of composites. And Tobias mentioned earlier on the requirement for thermal blankets or heat resistant blankets on the inside of the component. This is to protect the component itself, because on the hot side of the blanket, it's over 300 degrees Celsius. And without those blankets, you will degrade and destroy the component. Even a metallic interfix structure needs thermal blankets. Now, these blankets are heavy, and they will ultimately feed into the weight of the overall structure or their overall assembly. So we want to try and get that service temperature of the materials we use as high as possible in order to reduce the thickness of the blanket. And I'll talk a wee bit about that later on. So the main project objectives: evaluate multifunctional materials and the methodology to process these together, evaluate automated fiber placement as the automated process of high temperature resistant materials in order to improve process efficiency and reduce thermal blanket requirements. Design and manufacture the tooling that we need to produce the actual demonstrator. In doing so, or on the path of the demonstrator, produce an interim risk mitigation panel to close out some risks and manufacture the full-scale demonstrator itself. We will also, as part of the final, throughout the process and as part of the final demonstrator, validate some integrated care monitoring sensors for quality control. So now, the rest of the project partners will be discussing material evaluation in more detail, particularly the higher temperature resistant materials during their presentations tomorrow. So I'm not going to dive too much into this. However, I do want to just show a couple of slides highlighting a couple of important factors associated to material selection and how this affects the manufacturing process of the use case. So if we focus on the component architecture for a moment, the interfix structure is required to be a honeycomb sandwich reinforced structure comprising of a face and skin. You'll see on the top right hand image there, a face and skin, a honeycomb core and a backing skin. The honeycomb stiffened structures offer excellent specific strength to weight ratios, and they also offer excellent acoustic properties, and that's why we use them for this application. So within the project, multiple materials in terms of the carbon fiber reinforced polymers were evaluated in terms of max service temperature and their associated mechanical performance and thermal conductivity, which that'll be discussed in other people's presentations. In terms of the honeycomb cores themselves, now typically in aerospace, grade honeycomb cores are Nomex, which is aramid paper infused with phenolic resin, created into a honeycomb structure, or aluminium honeycomb cores. Now, both of these were evaluated. However, with excellent thermal conductivity a requirement, we did need to conclude that Nomex had to be eliminated because of poor thermal conductivity. Hence, we needed to focus on the aluminium cores. Now, the aluminium cores then, I'll discuss that in the next slide. They do create another issue, but if you can see here, the graph on the right-hand side, the middle column shows how thick the thermal blankets would need to be in order to use Nomex cores. So that's why it needed to be eliminated. On the left, you can see a typical metallic, the thickness of the blanket on a traditional metallic interfix structure, and our chosen carbon / aluminium core solution. So I mentioned an issue with using aluminium, and you maybe wonder why I'm terming galvanic corrosion and springback in the one slide, but they are related, if you can bear with me. So one critical issue of using aluminium cores with carbon fiber is that it immediately presents two of the foundational conditions for the onset of galvanic corrosion. So the bottom right here, I've stated the textbook definition of galvanic corrosion is an electrochemical process in which one metal corrodes preferentially when in contact with a different type of metal, and both metals are contained within an electrolyte, such as moisture and salt. So If we look at the table above, the galvanic series of metals the galvanic series of metals, you can see that aluminium is right at the top, at the anodic end, and graphite or carbon is at the opposite cathodic end, and hence the rate of corrosion between these two metals in contact with each other would be very high, and it would also result in catastrophic failure of the alloy core and hence the entire component. So it's a serious issue, and it's a serious risk, and one that has to be dealt with, and a solution to it dealt with immediately. So to overcome this, we can isolate the two materials using an insulating layer, and an industry-proven material which does work very effectively is glass fiber. So we can do that, and that is what we used within the demonstrator. However, introducing glass as well as using carbon fiber, this introduces another issue that we have to overcome, and that's in terms of spring back or change of profile during the autoclave cure. So carbon fibers, they have a CTE of close to 0, meaning they don't really expand or contract during different temperature changes. Glass fibers, on the other hand, they expand with higher temperature, and they contract again as the cure cools down. Hence, when these are bonded together and cured together, the glass can end up pulling the carbon fiber. For example, in the top left-hand image is a picture from years ago, where someone found out the hard way how well glass can pull carbon right up off the tool and close it in altogether. So it is a serious issue. So in order to prove this out and overcome the risk before we attempt to lay up and cure the full demonstrator, we needed to create a risk mitigation structure, importantly of similar sort of shape and profile to the final demonstration. So I'll just show you very quickly an overview of that. So like I said, we needed to incorporate or produce a panel of similar shape and size to our final composite interfixed structure demonstrator. So what we did was we utilized a full-scale tool and laid up a parcel structure which incorporated the full curvature of the center section of the component. Since this curvature will ultimately have a direct, proportional effect on any potential change of shape during the cure process, i.e. different degrees of material expansion and contraction. So the pictures here show you the step-by-step process that we carried out to lay up the assembly and prepare it ready for cure. So before we go on, just to see if the RMS cured successfully without any spring, I wanted to just highlight another important factor. We did need to optimize and evaluate specific cure parameters to do this. So with automated fiber placement in mind for the backend structure, the final process step of this demonstrator manufacture, we needed to optimize the vacuum and autoclave pressure levels of the layup prior to fiber placement over the honeycomb, etc., for the debulking process in order to ensure a smooth surface over the top of the honeycomb. So too low a pressure during the debulk phase will result in the glass not tacking correctly to the core. And too much pressure will ultimately create what we call telegraphing or golf balling effect. You can see it specifically where I've labeled vacuum pressure spec A. This has also actually caused this excessive pressure caused honeycomb crushing, which you can see on the left image there as an example. So the honeycomb crushing, that ultimately closes the cells. The specific strength of the honeycomb is very good in terms of the thickness of the Z direction, but it's not very good in the lateral direction. So we needed to evaluate optimum vacuum and pressure levels, and you can see how progressively from spec A to spec B to spec C, you can see the surface getting smoother and smoother, and on the right hand side you can see an image over a much larger component surface area where we applied the same spec, i.e. spec C, and this created a very nice surface, smooth surface optimum for fiber placement. Sorry, mouse moved a little too quickly there. So yes, so this is the final result of the risk mitigation structure. So with the vacuum and pressure parameters that we evaluated, these assigned and a carefully evaluated layup methodology, we did successfully produce the fully cured risk mitigation structure. There was absolutely no change of shape whatsoever, no spring. You can see particularly in the top left image that the component is sitting perfectly against the tool profile after the vacuum bagging was removed post-cure. And on the right-hand image, you can see the component sitting out of the tool itself. So this was a successful outcome and a step in the right direction in terms of the full-scale demonstrator. So the first thing we needed to do to produce our demonstrator is produce a cure tool, an outer mold line cure tool. This would be used for the layup and the cure of the component. So it's a bespoke tool. So depending, first of all, depending on the materials that we would use for the use case, we do need to, for the tool to be able to withstand up to 200 degrees Celsius and up to 6 bar of pressure. This is typically, maximum sort of parameters that you would use for the cure, no matter what sort of composite material typically used. So first of all, we immediately discounted a metallic solution since it would be extremely expensive and inefficient, of course, for a one-off demonstrator. And as discussed also earlier on, the difference is in CTE between it and also the carbon/glass would add even more complexity and risk. So let's look at some of the solutions that we thought of. First of all, tooling block. It's widely used within the industry. We use it here, although typically we would subcontract it out if we need it. This local specialist can produce these tools. So tooling block, it is a very useful material. It is very easily machined to a very high tolerance using CNC machines. It was considered to produce this tool. You can see on the bottom right hand side the dimensions of it, and you can also see actually the excessive weight. This would ended up being 2,750 kilograms just for the tool. So now the tooling block, it is very high temperature resistant, and it has a very low CTE, ideal for this. However, this material is extremely brittle. And we have found that out the hard way over the years. Most recently, actually, a couple of years ago, I seen a tool where it went through one autoclave cycle. It came out and went down a ramp when it came out of the oven, maybe a few millimeters high, and the tool cracked immediately. So, yes, this concept was decided not to go ahead. So the second concept would be carbon fiber itself. So we have vast experience here of producing carbon fiber tooling. It's extremely robust. It eliminates any CTE issues, and manufacturing in-house would save on cost, of course. Compared to the tooling block material, only 300 kilos versus the 2,750. That's a typo there. 2,450 kilograms lighter, I should say, so significantly lighter. The process would ultimately involve us producing, first of all, a master tool in order to create the surface and then create the tool itself. So again, because of our experience of doing so, we decided to go with this tooling concept. So just a couple of slides now to showcase the impressive work carried out by our tool engineering manufacturing facility here at Spirit Belfast to produce the composite cure tool. So step one was to produce the master tool, which will then be used to lay up and produce the OML tool surface. So the guys laid up multiple layers of tooling pre-preg, cured that in an autoclave in order to produce the master tool, which you can see on the top left image. That was it after it had been taken off the tool itself to produce that. Secondly, then, using the CAD model, the 2D templates of the egg box backing structure boards were printed and used to produce a timber backing structure. You can see in the middle image there, just to support the master tool while we lay it up onto it. And finally, just before we lay up anything onto it, the tool was bagged up and vacuum drop tested to ensure vacuum integrity, which it had passed successfully. Finally, then, unlike the master tool, we then the master tool utilised pre-preg materials, but the team decided to utilise and recycle some off-cut dry fabric material, which came direct from a composite wing factory just down the road. So a dry preform was laid up onto the new master tool, and it was infused and cured out of autoclave. Using again, like the last time, instead of timber, this time we used flat composite boards and used the 2D templates to cut out these boards and create a backing structure, which the tool surface was then bonded onto. And finally, before use, the backing structure was surface sealed. It was vacuum checked, and it again passed successfully. So great work carried out by that team. So finally then, I'm just going to summarise. I'll take you through a few final slides summarising the manufacture of the composite interfixed structure use case itself. And I'm going to follow this up with a short video montage. I think I'm more or less on time too, thankfully. So the initial phase of the component manufacture was carried out here at Spirit Belfast. This comprised of the hand layup of the composite facing skin, the honeycomb core preparation and placement, and finally preparation of the component for fibre placement at NLR, the Dutch Aerospace Centre in the Netherlands. So in the top left image, you can see the completion of these final manufacturing steps of a composite interfixed structure tool. The light brown colour is our facing skin, and then the what looks like a luminous or a radiant colour which is over the honeycomb core. This is the film adhesive that was applied over the honeycomb core, which assists the application on the tackiness of any subsequent materials. You can see all of this being laid up onto our new carbon tool. Also want to point out, before I'd mentioned about the risk of honeycomb core crush. So in the previous specimens that were used in those trials, they had 90-degree edges. Now what we did was we applied periphery bars around those to stop any core crush, but of course we can't really do that for this application. So what we did was we created ramp ridges all around the edges of the component and in these access panel areas. And the edges are twofold. They enable the fibre placement machine to smoothly roll from the face and skin up onto the honeycomb core. And secondly, during any A, autoclave pressure, and B, the pressure of the fibre placement head itself, or the roller, with the ramp, the pressure applied perpendicular to this honeycomb means it's able to withstand the pressures and no core crush exists. So this was a very successful approach. So on the right hand side, the tool was then shipped off to the Netherlands, to NLR. You can see one of their guys here setting up the tool onto the fibre placement machine. So in this case, it's a Coriolis C1 machine. A lot of experience. Everyone, familiar with fibre placement, or indeed fibre placement of these type of structures, will be familiar with this machine. And in this case, what to do? It's a fibre placement machine utilising an industrial robot with an end effector on the end, a rotational positioner in the middle where the tool is fixed to, and the rotational positioner moves as well as the robotic arm in order to deposit the material onto the surface of the tool. So NLR, they were responsible for the fibre placement, so I'm not going to get too much into that. Wilco Gerrits and the team will provide more information on fibre placement. However, it is important that I do show you some images of the fibre placement in a subsequent video, which I'm going to do now. I will point out, however, that NLR, of course, carried out multiple layup trials using different materials on the flat, really, before we decided to go ahead with the final demonstrator. So here we see some images of the tool itself fixed onto the rotational positioner, and the fibre placement machine starting to deposit material onto the surface. So first of all, you can see here the deposition of the material. The tackiness of the material was excellent. The accuracy of the fibre placement machine was equally excellent, specifically on specifically on the first ply, of course, which you can see here, the first layers down. Now, I will point out the complexity of this tool. It has a direct effect on how the machine is able to perform, and the complexity of the profile itself, and as well as that, the fact that the machine needs to lay up over the honeycomb cores. These are all significant challenges for fibre placement as a technology. So material attacking this is absolutely key. The other thing I'll mention is one of the features, the access panel areas there, where it does ramp down onto the facing skin, because it's has a shape that's curved. You can see on the top. I don't know if you can see my mouse here, but basically the curvature of that all the way around, including the ramps, and the fact that the material has to be deposited in different orientations, in 0, 90, and 45 degrees, did absolutely create some challenges. However, the guys at NLR were able to come up with some solutions which we were able to get around. And the other thing is the choice of material width here was key, because with fibre placement you do of course need to weigh up optimum material width versus deposition rate, since the wider the material, the increase in deposition rate, but the accuracy and the effectiveness of depositing that material over complex shapes gets more and more difficult. So the other thing too was the mold was extremely challenging in terms of space, and we did find this out almost the hard way, but nothing was damaged whatsoever. In the middle picture you can see, well, hopefully see, probably in the right hand picture actually is better, sort of a silvery coloured rectangular. It's a fixed structure on top of the machine in order to guide the grey. I'm not going to use the right terminology here, so apologies to NLR, but it guides the material that's fed through the toes or fed through the top. I'm going to call it a hose down to the end effector of the machine. This rectangular structure guides it away, but it wasn't included in the fibre placement programming software at this point in time, and hence it wasn't able to virtually predict where in space that fixture was. And you can see in the middle image where we did have a light collision. So the only quick solution to that was we simply removed it, and that solved that issue. So but considering it wasn't included in the virtual simulation, we can't really suggest that there was any issue with the prediction of the fibre placement. So a few more images showing the fibre placement at its completion, really. Everything was completed, all the layers that we applied and all the orientations were successfully completed and on schedule, so well done to NLR and the team for that. And in the picture in the middle, you can see myself on the left and Nikos from Synthesites showing off there. So the next stage of the process then after fibre placement was the actual autoclave curing. So we utilised the help of Fokker GKN up the road in the Netherlands, simply because the autoclave at NLR just wasn't large enough. So a big shout out and thank you to those guys for supporting us with that. There was absolutely no issue. So we utilised one of their production autoclaves. And you can see Nikos in the middle picture on the right hand side, and his online cure monitoring technology on the bottom right hand corner. Nikos is going to talk a wee bit more of that, but that technology was successfully used, and successfully used in order to reduce the cure cycle that we actually carried out for this demonstrator based on previous trials. So as I said, Nikos will take you through that in his presentation. And finally then, yeah, I'm sort of a little late here, so I'm going to speed up. This is the last slide. A successful output to our composite use case, interfixed structure use case. You can see it on the left hand side, the tool, the cured component after the vacuum bagging was removed. And you can see the shape of the component is sitting very nicely against the profile of the tool, so no component distortion or spring. Then the middle image and the top right is after we had finished trimming it at Spread Aerosystems. Again, the inspection of the component looked excellent. There was absolutely there was no disc bonds either, and there was no porosity. And you can see on the image on the bottom middle just how well the fiber placement process was able to compact over the honeycomb core and bond then to the face and skin at the top end. So a very, very nice outcome of that. And again, the right hand image there again showing how smooth the ramp region is. At the edge of the core, excuse me. So that is the end of my presentation. I know I'm a wee bit late. Hopefully there'll be the time for a couple of questions. But before I move on to that, I'm just going to show you a video montage here. So if you bear with me, I will get that set up here. Can everyone see the screen here?
Yes, it's well.
And could you hear anything there, Tobias?
No, I can't.
So, can you hear that?
No.
No. Apologies.
Daniel, did you optimize the audio?
I did.
When you click on the button share, you know, you have this this list that you should scroll down and use the last option normally.
Yeah, optimize for motion and video.
Yeah.
That's what I've clicked on.
Okay.
Share. I think now?
No, I can't hear anything.
That's strange.
Yes, it's strange. Do we need the audio? Or?
It certainly helps to be, yeah. If you bear with me for a second, hopefully
of course,
we'll
take
get
your time,
this sorted.
please. So meanwhile, I can see that there have been already 3 questions in the chat and in the Slido system. Thanks for using it already. And so after the presentation, then I will come back to those questions so that we can clarify, give you more feedback. You may use it in an anonymous way. If you like your name to be displayed, then you have to explicitly do the settings to display the name, just if you like. It may be the case that the Slido system requires some special updates of software. So if it doesn't work for you, please just use the conventional chat and then we can copy it into the Slido system.
So I'll try and play again, Tobias.
I keep fingers crossed. Yes, thanks.
Does that work?
It works.
Yes, it's working now.
Excellent. Okay.
Okay. Thank you, Daniel.
Okay. Thank you, Tobias. Hopefully, maybe you have opportunity for a couple of questions.
Yes, I think we should take the time for questions. And I would propose that I just read them here, except that the lady or guy who has written it down would like to ask them directly themselves. I may read first. So one question is that you may come back to the material system, the resin system that has been used for the demonstrator. I mean, we have been considering different resin systems inside this project and also investigated for your use case. Maybe you can come back to this question, which has been used for the CFRP tool in this case. So not for the demonstrator, but for the tool.
Yes, in terms of the tool itself, it's typically used tooling prepreg, which was used for the master tool. And in terms of the cure tool itself, like I said, we utilized some dry fiber recycled material from one of our other factories, and then infused it with a typically used tool fusion tooling resin system.
Mm-hmm. I hope this is answering the question. Another question that was asked was if 3D printing was considered at the beginning also as an alternative solution for manufacturing the tool.
3D printing was not. I don't believe that anyone in the consortium, and I could be wrong here, has that sort of size of additive manufacturing equipment. It's something that we are very interested in, I must say, here in Belfast, and something that we're hoping to get into in terms of tool manufacture soon. But we don't have that facility at the moment.
Mm-hmm. So is there any interest for you to get some information on this? So should somebody come back to you regarding this? So if you would like, you can always contact also Daniel directly. If there's any idea to support here.
Mm-hmm.
I would like to come to the third question that was mentioned was regarding the edge sealing, if that was managed at high temperature as well to perform edge sealing.
So would the person like to maybe clarify what the mean edge sealant of the final component, or during cure, for example, or what are they referring to?
Would you like to unmute and rephrase your question, please?
During the preparation.
Oh, okay.
Okay. So yes, we again found out in the past the hard way. Typically autoclave used edge sealant does have a maximum temperature. It's probably around no more than 200 degrees Celsius. So, however, at no point did we need to go above this temperature. So the typically used edge sealant was fine. It in correlation with normal vacuum bagging was perfect for the process.
Mm-hmm. There are many more questions here, and one was that you could confirm again, please, the manufacturing steps to tape a few layers at first of the laminate and then manually place the core and then again do the tape laying of the remaining plies. Is that maybe you can explain again, please?
Yeah, exactly. So what we did was we laid up the face and skin using a hand layout process and some pre-preg. I know this people here is asking what the material is, but I'm not going to disclose what materials we used or the cure parameters, since it's intellectual property of the consortium, and we're quite protective over that, what we used. As will be mentioned in the rest of the presentations, there was a number of materials that were evaluated, and there was a number of materials that were eventually used, but it's certainly part of the development, and that's why I don't want to get into disclosure. But in terms of the processes, we laid up several layers of pre-preg material. We needed to cure that off, first of all. That's stage one of the process, and the reason we need to do that is because the face and skin on this application has to be perforated, and because it has to be perforated without damaging the honeycomb core itself, we perforate the face and skin first, and then we bond the honeycomb cores after that, because if you apply the perforation process after that, you can damage the core in behind it that's bonded to it. So step 1 was lay up and cure the face and skin. Step 2 was to tack the honeycomb core kit in place. By the way, the honeycomb core kit already is, at this point, has the ramps applied to the edges. It's pre-fitted by our team that are well used to doing this process. It's a complicated process. And then it's bonded in place. Now, not cured, but tacked in place using film adhesive. And then subsequently, we laid up another layer of film adhesive and the required glass for isolation purposes. And again, we didn't cure at that point. We want to reduce the number of cure cycles in order to make the process as efficient as possible. So at that point, then we shipped the tool off with the layup, the wet layup, I'll call it, over for fiber placement, and NLR then proceeded with the fiber placement and the final cure. So overall, a 2-stage cure process.
Right. Since we are already 8 minutes behind, I would just like to have one last question, because you also mentioned again the perforation step, and I would like to maybe come back to this question and the others. I would propose that we collect the chat, and Daniel, that you may have the chance to answer those questions later on.
Okay. That's
so
fine.
here there was a question about the perforation, how the perforation of the CFRP layers has been done. Maybe you can give information about this, and then we could continue with the next use case.
Yes, so we didn't use the traditionally used mechanical drilling process, which we also have and use on site here. We have been looking at a sort of an innovative grit blasting process, but it's not our technology, and I can't really disclose any more than that.
Right. Okay. Thank you very much for using this system. I hope you have understanding that we can come back to you with your open questions, that they will not get lost. But I would like first to continue with our agenda and like to invite Inigo to come on stage. So to say, unfortunately, we are not physically on stage. Everyone is in his own office, and it's a little bit strange, but I'm happy that we can do it anyway and have such a large audience and come in contact with you. So Inigo Ortiz de Sarasate has been now a stress engineer already for 25 years, and his professional development in definition, in execution and analysis of structural tests, which starts in the development phase and goes up to the certification of aeronautical structures. And in his position, he has already participated in quite a few European projects, namely COCOMAT, Nice Trip, or even Clean Sky rear end projects. And now, Inigo, thank you very much for preparing the presentations together with mainly Christian Brauner and contributing of other participants. So I hope audio connection is working, so you can give it a start if you like.
Okay, thank you very much, Tobias. Can you hear me? Can you see my
Very
screen?
well. I can also see screen, both works.
Perfect. So good afternoon, everybody. My name is Inigo Ortiz de Sarasate, as Tobias introduced. And I will, together Christian Brauner, a professor from the Northwestern Switzerland University, we will present all the activities related to the ARNOVAT use case within the SuCoHS project. Brief agenda, briefly the agenda. I mean, I introduced the use case principles, the objectives that we had from the beginning of the project. I will also deal with the building block approach design to validate the fire analysis methodology. Also, Professor Christian will present the details of the manufacturing of the demonstrator. And subsequently, I will present the details on the fire certification, fire test campaign and other related tests to provide the data for our models in the simulation. And I finally will provide some view of the objectives met and the next step after the SuCoHS project. So there are no use case principles. Okay, initially at the beginning of the project, what the objectives that we envisage to be achieved through the collaboration, through the participation in this project, was the weight optimization by the use of novel composite materials with present improved thermomechanical and fire capabilities that allowed reducing all the thermal and fire barriers on the IPU surrounding structures. I mean, the use case, the objective from Arnova was the Telcon and all the system associated to the APU system. I mean, associated to the reducing the thermal barriers, as I mentioned, reducing the thermal blankets in order to achieve that the composite structure, the composite structural part not be affected by these high temperatures. So the development of new materials, we foresee that could suppose a good improvement in order to achieve these weight optimization objectives. On the other hand, another big or interesting objective that we have from the beginning was to develop and also I mean, to face a development by supported by test of a simplified fire simulation methodology that could help us in the fire certification test campaigns by gaining understanding to design the fire certification test campaigns, and also by reducing the development associated cost regarding the development test and even certification test, which are normally in the past, normally Arnova goes to the test campaigns without having any aid, any assistance from the simulation, from any Arnova doesn't have any prediction capability, and gaining knowledge on and understanding on the heat transfer process associated to the fire events, and to understanding the degradation process associated to the fire events would be very interesting and for sure well-used information regarding the design of the certification fire test campaigns to comply with the requirements. So as being these two main objectives in mind, a lot of collaborations emerging within the SuCoHS partners in order to satisfy all the common objectives. Collaborations for developing the new material, as Tobias mentioned at the beginning, and also collaborations to develop and substantiate and by test this the methodology, the fire analysis methodology. I will talk a little bit more about this the methodology in these sections regarding the building block approach that was designed or defined for the fire analysis methodology. I mean, a test pyramid was defined thanks to the capabilities of the SuCoHS partners, mainly DLR and Onera, to support the fire analysis methodology. This test pyramid was trying to accompany each of the analysis development stages. I mean, meanwhile, we were understanding the heat transfer problems. Meanwhile, we were understanding the degradation reactions happening due to the exposure of high temperatures. We were including the models into the methodology, and also we were validated this model. Mainly, the more important point was to understand and to understand what's the physics behind each of the thermal response of the composites, and also to take that understanding to the models. So, as I say, thanks to the testing capabilities, mainly focused on understanding of the thermal response and of the composites, we could design and execute different tests of different levels, just covering some parts of the simulation development that we were facing on. So, for example, I now will detail some of the tests. For example, in level 0, there were quite a few tests to characterize the basic mechanical capabilities at high temperatures, and also the thermal parameters of this novel material. In the level 1 of the pyramid, we could understand, thanks to the thermogravimetry tests, and thanks to the test capability thermogravity test from DLR, and thanks to the Onera thermal testing camera called Blade, we could understand how for this novel material, how the evolution of the thermal parameters with the temperature is. We could take those parameters to the models, and also we could understand the kinetics and energetics of the decomposition associated to the thermal degradation of this material. We also, thanks to again to Onera testing capability of having a fire response of thanks to the fire facility that Onera disposed, we could understand firstly understand what was the fire response of this novel material, and we also at this point we saw some promising capabilities, promising response regarding, for example, with epoxy-based composites. We saw that the outgassing were significantly reduced, we saw that regarding comparing with the typical epoxy composites, the temperatures of the back face were lower, and so we saw that this material could be really efficient, or at least more efficient than the typical epoxy system in terms of thermal or fire barrier. So now, Christian, please, maybe you can hand over. Christian? Okay, don't know. Christian Brauner, Professor Christian Brauner was supposed to present these slides, but...
Christian, do you have your microphone switched on?
I can see that Christian is not muted, at least.
Can you hear me?
Yes.
Yeah, no,
Oh, yeah.
Perfect.
Hardware muting. Okay. No, we can't anymore.
Everybody? Can you hear me?
Yeah.
Yep. Thank you, Inigo. I'm just jumping in. So hello, everybody. I shortly would like to present the manufacturing of the demonstrator, which was later used in the fire tests. So it was a stiffened panel, which you can see here. And related to the material development which we performed on this material, we used the cyanide ester system, which was modified due to the curing behavior to fit to a normal autoclave. This was special because for cyanide ester systems, you typically need higher temperature than the standard autoclave temperature of 180 degrees. Then this material was as well toughened, and we converted it together with the company NTPT to a thin ply pre-brick with an area weight of 60 GSM. And we performed as well manufacturing using AFP, but this demonstrator was done in a hand layup. And due to that, our first demonstrator, a risk mitigation panel, showed some defects in the T-section areas. We evaluated different settings at the T-joint, which you can see here a little bit. And maybe, Nico, you can go to the next slide. So here you can see a simple or the setting which we used in the autoclave, and also some illustration how we have done the preforming. So we performed simple cutting, and then this T-section were built by shaping some U's or T's, and then everything was assembled in the tool, and it was cured in a medium-sized autoclave at our facility. And we used as well the Q simulation method, or the Q simulator from Nikos Pantelis from Synthesize, to display the curing process outside. Then on the next slide, please. Here you can see the final structure, which is used later in the fire test. And as mentioned in our first risk mitigation structure, we observed that we had some cracks and failures already after manufacturing in these T-section area. And therefore, we performed a comprehensive study supported by some process simulation to understand the residual stress and process-induced deformation, and from this we derived one setting where we had no failure in these section. And if you are more interested, there's also some literature, some publication about it from the Sample Europe Congress, as mentioned here. So if you have more questions about the manufacturing or the material itself, so tomorrow there will be one session about it. So thank you, Inigo.
Thank you, Christian. So next point is presenting the details about the fire test campaign on the Arnova use case demonstrator. So, as I mentioned before, 3 tests comprised the fire test campaign. The 2 first tests was focused on providing some experimental data for simulating the flames, so for the flame model to be used in the simulation. The first one was to obtain a temperature spatial field of related to the flame. For this, a titanium panel with the same dimension and curvature of the composite panel was instrumentated with a bunch of 26 thermocouples, and okay, all the readings provide us along 15 minutes provide us information about what were the flame temperatures around the panel exposed area. Second test was similar. Where the objective was to determine the heat flux spatial field associated to the burner, to the certification burner. And for this, we took 84 readings covering the flame influence area. And finally, the fire certification test on the Stephen panel. The Stephen panel that was representative of an take-on structure, take-on structure surrounding the APU. The material was the novel material developed in within the SuCoHS program, and we try to fix to the fire certification requirements following the regulatory associated to the fire certification test. So we studied what was the worst scenario for fire event associated to the APU. This was an ground condition with 15 minutes fire test, so it will be a fireproof conditions, and with load with loads associated to that condition. No credit for external flow consider, okay, so we went for a certification test in the same way as if this was this would have been a certification process. So we instrumented with 26 thermocouples, the backside of the panel, in order to provide data for the final validation of the fire simulation tool. By the way, I didn't say it before, but tomorrow we will provide the details regarding the fire simulation methodology developed within SuCoHS. So this is a picture for the first of the tests that I mentioned, the test to measure the temperature spatial field associated to the certification burner. These are the results and the temperature results of the 15-minute test in the titaniums over the titanium plate. a picture regarding the test where we obtained a heat flux map associated to the certification burner as well. As I said, this data is to feed our flame model, and tomorrow we will explain that. And okay, regarding the preparation for the panel to face the certification test, we prepare exposed windows appropriate to coverage the flame as per the regulation. The rest of the panel were protected with thermal blankets. And as I mentioned, 26 thermocouples contact thermocouples were installed on the back face in order to provide temperature data along the test. The test setup was designed in order to allow for a load application with, as you see, an actuator and system of pulleys that to apply tension load over the panel through a fastened joint with steel plates in order to load transfer. Everything, all the systems have to be protected against the fire, against the heat exposed by the test. And as there were, I mean, this is a typical installation. This laboratory normally is certified for the fire certification test, so comply with all the requirements to face this type of test. Prior the test start, the flame have to be calibrated in temperature with a rack of 7 thermocouples, and the heat flux also have to be calibrated to ensure that would comply with the requirements. And okay, I have several videos here, quick videos to show the evolution of the test, but just I can advance that the Stephen panel successfully passed the test, so there were no elongation of the structural or no elongation or a structural failure for 5 minutes loading, what was the load requirements. No one through after 15 minutes, or no axial ignition after 15 minutes. Sorry, I have to. Get this. Let me to show. Okay, this is a 1 minute video just showing the first approximation of the burner with the panel. As you see, around 20 seconds from the beginning, the combustion of volatiles start to being produced, and I mean volatiles coming from the outgassing of the composition of the composite material. This volatile ignition lasts about 3 minutes, and from that, a stable response was obtained. I have another quick video of the 5-minute testing when the load was, when the unloading took place. You see now the flame is stable, and the same for 10 minutes. Same flame has shown to be stable, and this is the last just seconds of the test after 15 minutes test, in which okay, we can see that the flame keeps stable, and And okay, the panel successfully passed the test, as can be also shown in this last video from the backside. Video of the last 20 seconds of the test, in which you see after the test ends, now burn through or backside initial were produced. So this is what the burner keeps back. So similar observations that we saw in the fire test, in the Onera fire test, or small outgassing, smaller outgassing than observed in the epoxy system, small volatile ignition, and even small temperatures at the back face regarding other similar tests with subjected to the certification conditions. So the temperature at the backside was around 15 degrees from the 1000 degrees that is the temperature at the front face. So it seems I mean it's verified that this material is a good fire barrier.
Excuse me, Nico, could you try to finish your presentation?
Yeah. So very quick. This is these are the status of the panel, and minor decoloration around the fasteners, but okay, successfully passed the test. More pictures or more regarding the status at the end of the test. And okay, just to finish, let me present that the objects were met. So this novel SuCoHS developed material shows promising capabilities for designing for challenging thermomechanical applications, are also for complying with fire response requirements. Special mention to the significant fire response improvement observed regarding the epoxy-based composites. The two previous points represent a good starting point to consider this type of material and construction with the aim of optimizing structures around the power plants. That was one of our main objectives from the beginning of the project. The building block approach used to support and validate the empirical simulation methodology has proven to support adequately different development phases. Tomorrow, together the presentation of the fire analysis methodology, this also could be checked. And just to finalize my intervention, I have to say that the simplified semi-empirical simulation methodology shows promising capabilities for gaining knowledge about the fire response of susceptible details that assist the sizing, to assess the sizing. Capabilities for selecting critical details under fire requirements to reduce the certification testing effort, and also to reducing the development testing effort by itself, and in assisting in the design of the certification test. So okay, that's all. Sorry for took a couple of minutes more than my time, and thank you for your attention.
Yes, thank you very much, Inigo. We have been starting a little bit later with your presentation and now took a bit again. So we are in a situation that we might have to shorten, or I think we do need to shorten our coffee break by 10 minutes. I hope this is in alignment with your interests. I can see from the chat also that there are two questions regarding the T-intersection, how noodles can be used or have been investigated. And the second question is on the certification requirements for that test scenario. And my proposal is that we that you can answer the first question regarding the T intersection also in the chat, and regarding the certification, this is something that fits very well to the to the panel discussion today, because then we're also talking about certification requirements, and I think we can come back to this. And if not fully answered, then we can also do it after the session. But I would really like to continue with our presentation so that coffee break still exists. Thanks, hopefully, for your understanding, Inigo. So that's why I would like to hand over to Paolo Balocchi from Spirit Aerosystems. Sorry, Collins Aerospace. And Paolo, we also know each other quite a long time now. You've already 25 years experience as well in R&D, mainly aerospace. And you've been a general aviation chief engineer. You've been a jetliner principal engineer on the composite wing development. I think we know what you mean. And now you are a senior manager from composite structures at Collins Aerospace. So that is your current situation, and you've been also involved in multiple papers, conference talks, owner of several patents, and also involved in other projects, European projects, as well as a coordinator. So now, please, I'm happy to have you here presenting the third use case in this case. And also for everyone, use the chat in order to ask your questions. Thanks.
Yes, Tobias, thank you very much for the introduction. And can you hear me all right?
Very clear, thanks.
Okay, thanks very much.
Yeah.
Good. So we'll try and stick with the 30 minutes. So you see what was here in the title, what was our target for this program. And this is the target that we chose based on the goals, if you want, which we received from our organization. And the goals for us and the research and development are often the same, if you want. So lighter, parts need to be lighter, needs to be cheaper. But now we have new requirements. We need to move into new materials, new families of materials like green, renewable source, or recyclable even. And also because obviously here we're talking about composite materials, we need to move towards technologies that are more in line, particularly for interiors, with the high rate of production that we need to supply components to the interiors market. So moving towards, for example, robotic layup and or robotic technologies. So what we did choose to develop the new concept or the next generation of composite shells for business class or the premium cabin anyway, is the baseline that is represented here in this slide. You see these on the left. You see just a simple, blank, if I want, a composite shell, because obviously we couldn't show anything for confidentiality with our customers. But very timely, last week, Finnair presented this new family of business class, and in the words of the press, it is a seat like no other, not only for the shape of it, but for us designers, structural designer, it is new because it's the first one where the shell is actually working for the structure. So the composite shell is not just a shroud or a furniture, but it is part of the load path, if you want, in between the occupant, hence the seat belt that you see here, and down to the floor connection and reaction. So this was our baseline. The way we tackled this is through three different areas, if you want, three different disciplines. First of all, we did look into new structural concepts. So up to now, this generation of this type, if you want, of structures have been built with the conventional honeycomb structure. So honeycomb sandwich with skins on both sides, similar to what Daniel was showing earlier, or typically of what you see in some general aviation aircrafts or what you see in motorsport. But that's not necessarily the right approach for this type of high rate production and parts. So we looked into ISO grids, or we looked also into reinforcing the shells or the skins, monolithic skins, only where is required by the load path. So this is the principle. The other line of development is working closely with our capable partner down, particularly at NLR, in terms of robotic manufacturing and using AFP, something that has to be mentioned. We have been doing for a few years now in different European programs. The third area is the work with another partner, TFC in Belgium, at the development of supporting the development of something was already existing in terms of renewable materials, biomass. All these three areas converged into a classic pyramid of development where you go from subcomponent into the specification structure and demonstrator. And any work or any project is only as good as the team around it. So I'll, in here, I just quickly introduce Nigel McKibben that has supported this from a management and the business point of view. Deepa Jose, she has been leading the discipline of materials and process engineering. Pavlos Tranakidis leading the composite structural design for us. And Andy Blackwood looking into manufacturing engineers. And I'm quickly leave you with them. All yours, Deepa.
Thanks, Paolo. Hello, everyone. My name is Deepa Jose. I am a materials and processes engineer from Collins Aerospace's Interiors Central Engineering team. We are Kilkeel, Northern Ireland based. So towards the development of this monolithic structural composite shell by AFP process, my role was to steer the material development and conduct mechanical testing to support design and structural analysis. Next slide, please, Paolo. So this slide gives an overview of regulatory and OEM certification requirements for a structural polymer matrix composite shell. When it comes to FLAM, the requirements are vertical burn 12-second, Ohio State University heat release, and smoke density. This structural composite shell got shared load path, which Paolo mentioned earlier. So a B-basis design allowable is required to substantiate changes. In addition to B-basis design factors, we have to consider 4 additional factors: environmental, material variability, manufacturing defects, and impact damages. These factors are then used to develop knockdown or overload factors. Next slide, please. Our baseline material is an FST epoxy 2x212 carbon fabric material, which we already used in making structural sandwich composite shells, which Paolo showed in the beginning of this presentation. In SuCoHS program, we received carbon UD tapes of the same FST epoxy resin and made AFP compatible UD toes, then completed coupon level and subcomponent level mechanical testing. We also steered development of PFA resin-based polymeric metric composites. This work was done by Transference, one of the SuCoHS consortium partner. You could hear more details from Transference team tomorrow about the PFA developments. The advantage of PFA-based polymeric matrix composite is that the raw material for the PFA resin comes from the sugarcane industry waste. 3 generations of PFA resins were formulated, and based on mechanical and FLAM studies, 2nd generation PFA formulation was down selected. In the upcoming slides, I'm going to quickly take you through the coupon level FLAM and mechanical studies done on our FST epoxy and PFA polymeric matrix composite material. So in this slide, the take-home message is that when it comes to FST compliance, PFA shows superior properties compared to FST epoxy resin-based laminates. However, PFA matrix dominated properties are not that great. For example, interlaminar shear strength is down by about 40% compared to that of epoxy composite. Next slide, please, Paolo. In this slide, we are comparing the UD laminate made of FST epoxy and PFA. This FST epoxy coupon plate was fabricated by AFP process at NLR. PFA UD material had some initial tack issues, and also we couldn't make the coupon plates by AFP process. PFA UD plate was hand laid up. And as in the case of the fabric material, fabric laminate, here again, the UD PFA laminate shows a similar drop in interlaminar shear strength. Next slide, Paolo, please. Yeah, so this slide, it captures the dynamic test. So we have done this dynamic test because the structural composite shell needs 16G dynamic tests pass as part of certification. So these studies were coupon level dynamic studies were done at Onura. In summary, both epoxy and PFA coupon level dynamic tests demonstrated a better shear performance for these materials under dynamic loading conditions. Next slide, please. Paolo. We also carried out some cyclic fatigue test again at Onura for both PFA and epoxy material. Cyclic loading did not show any impact on shear strength or modulus of epoxy material, whereas in the case of PFA material, cyclic loading showed a slight effect on shear modulus. Next slide, Paolo, please. So this slide captures a quick comparison between epoxy and PFA resin-based composites. When it comes to sustainability, PFA is really good. In a cost perspective also, PFA is better compared to FST epoxy material. When it comes to flame, heat release, and smoke density, again, PFA is excellent. However, there is still need for improvement of matrix-dominated mechanical properties like interlaminar shear strength for PFA. Being said that, we still could design for PFA parts with the mechanical data available as of now. When it comes to maturity, PFA is mature enough to make structural composite parts. In our case, the final demonstrator here we made in FST epoxy, as mechanical properties for PFA was not available during the demonstrator design phase. However, we were able to demonstrate the maturity and manufacturing suitability of PFA based on PFA-based polymer matrix composites by making risk mitigation structure. So that brings to an end to the material selection for Collins Aerospace's end use case. Now, Pavlos would take us through the design aspects of this monolithic structural composite shell. Over to you, Pavlos.
Thank you very much, Deepa. Hello, everyone. My name is Pavlos Tranakidis, and I'm a structural engineer in Composites. I'm going to take you through the design process of the new composite cell and explain the different stages of the design evolution and how it culminated in the final parts, which you can see here. Next slide, please. Next. Our goal was to develop a new structural concept to substitute the existing sandwich structure, a honeycomb core with carbon fiber skin, which you can see at the bottom right corner on your right-hand side. The new cell will have carbon fiber stringers as the stiffening load-carrying members and the thin skin to support them, as you can see in the same picture on your left-hand side. We worked on the optimization of one composite cell in this heat assembly. The first step was to identify the critical load path by using topology optimization. After that, smaller elements were designed at the subcomponent level to extract flexural material properties of stringer stiffened coupons out of bending tests. And then there was the risk mitigation structure, which was used to validate our models and integrate different manufacturing features and constraints in our design before proceeding with the manufacturing of the final demonstrator. Before I continue, I want to say that DLR supported the first stage of this analysis. The material used in all stages for manufacturing and tested was carbon fiber, FST epoxy, UD, or woven fabric. All the manufacturing took place in NLR and the testing in Kilkeel, Northern Ireland. So I'm going to start from the subcomponent 4-point bend testing. After conducting a parametric analysis, which is not included here, an equivalent design in terms of stiffness and weight to a 2-core-2 sandwich coupon was a component with a thin skin and 2 stringers 9 mm in height each. Next slide. At the first set of coupons, both the skin and the stringers were made of carbon UD, but the tool used for curing was different. In the first case, it was an aluminum tool, and in the second case, a rubber bag. The circle in the 4 deflection curves on your right indicates the ultimate strength of the baseline sandwich coupon. You can see that both in terms of strength and stiffness, the coupons cured with a rubber bag performed better. But in both cases, the stringers detached from the skin, and both the skin and the stringers failed. Next. That's why we decided to test new coupons, but with a skin made of woven fabric this time. 4 different techniques were implemented to improve the bonding between the skin and the stringers, as you can see in those pictures to the left. In the first one is our baseline. In the second configuration, we used carbon filler in the corners. In the third one, there is a woven glass fabric ply built up along the vertical faces of the stringers. And in the last one, there's an adhesive layer between the skin and the stringers that's not quite visible. Yeah, here. Thank you, Paul. Next. As you can see from those pictures, the skin didn't fail during the 4-point bending and the stringers didn't detach from it. So we decided to proceed with a woven fabric for our skin. Next. It is essential to have in mind that stiffness and strength as absolute values are not a criterion to choose between the different configurations, but is the stiffness to mass and strength to mass ratios which drove the decision on which technique to select. So after comparing the performance and assessing the manufacturability, we decided to proceed with the third option, the woven fabric ply on the sides. Next. So topology optimization is a mathematical method that optimizes material layout within a given design space. So in our case, it's the green area for a given set of loads, boundary conditions, and constraints in order to maximize the performance of the seat. The design loads in our case were 2. The static outboard abuse load, 300 pounds, which is normal to the surface at the application point, and the inertia seatbelt load, 1200 pounds, which is applied on the backside, and it's at a 25-degree angle with a normal. Next slide. The optimization for composites is a quite complex and time-consuming method. That's why we used some approximations and made some assumptions. The design area is considered as a quasi-isotropic material for the purpose of the optimization. By applying as constraints the displacements from the analysis that has already been done for the thin air assembly, the algorithm showed us for each load case independently, but also for both combined, what's the critical load path, as you can see in those pictures. So after translating those results into a new design, you can see in the central picture the first cell we generated. Next. Here you can see the latest design of a composite cell and the assembly. It's important to mention that the second cell of the assembly, for the purpose of testing, was manufactured with the existing technology. Next. The risk mitigation structure was made for 2 reasons. The first one was to validate our FEA models and our approach for the analysis of a stringer stiffened cell. And the second one was to test different manufacturing features like the steering radius, the crossovers, the ramps, etc., and identify any constraints and limitations. So the RMS was pulled forward by that metal plate, and those stringers in red detached from the skin during the testing. Next. So in our model, we expect to see high interlaminar stresses in the area of failure, but in our analysis, the stress did not exceed our material allowable. The static analysis did not indicate other than the bonding of the stiffener or the damage progression. So this is still a work in progress, but we extracted some useful failure indices using the Hassens criteria, which helped us validate the structural integrity of the demo panel. Next. So now we're moving to the final demonstration, which is the left half of this assembly. Next. Three different load cases were scheduled for testing. The first one was the outboard static abuse load, where we loaded it up to 50 kilogram force in order to validate our FEA models, and we will show you a video about it later. As far as the inboard load case is concerned, significant buckling of the skin occurred during loading, which requires further post-buckling analysis before loading it further. It is the picture on your right, as Paolo showed you. The seatbelt load is scheduled for the upcoming weeks in our facilities in Germany. Next slide. Here you can see in that video the loading of the final demo up to 50 kilogram force and then the unloading. Thank you, Paul. Next slide. So you can see here the measured force displacement curve versus the predicted displacement from our FEA models, which are the blue circles. You can see that the error is less than 10% for every instance measured. Next. So DIC, the digital image correlation is a 3D full-field non-contact optical technique to measure contour, deformation, and strain on almost any material. So by acquiring two or more images from different cameras in different angles and matching them by applying statistics and mechanics, we can extract the strain field. Our validation was based on two different fronts. We are talking about the outboard load case here. The first one was the principal strain, which is the maximum strain possible on a structural element. The FE analysis on the outboard load case indicated a 0.31% strain on the top of the stringer, which is its compression side, which aligned quite accurately with the extracted strain field from the DIC. You see it's 0.3 to 0.35%. Next slide. The second front was the normal X strain, which is the strain in the direction of the stringer following the material zero orientation. By placing a virtual strain gauge on the stringer, we extracted the 0.21% normal strain. It again aligned quite accurately with the 0.2% we extracted from FEA. The problem is we don't know yet which one of the two triggers the failure so that we can proceed with confidence to higher loads. We expect the results from the other load cases will shed light on that, and we will be able to predict failure. That was me, and I will pass it to Andy right now.
Good afternoon, folks. Andrew Blackwood, as a manufacturing engineer, I was responsible for the detail, laminate design, modeling, generation of supply data, etc., both in terms of just creating a balanced layup, etc., and incorporating manufacturing requirements. So a lot of that carried out a lot of advice from NLR. So thank you, Robert and Wilco, for your assistance throughout this. Also then did the tool design and sort of oversaw the manufacture again in conjunction with NLR. So next slide, please. Just a first note on the design, some of the key things that AFP has enabled for us. The first one in terms of both weight, structural efficiency and cost is the ability to net lay up local plies, frames, etc., particularly in terms of not requiring the same excess as a manual layup, and same trim excess, I should say, as a manual layup. We're also able to incorporate steered plies as shown on the right. So this provided a sort of a neat reinforcement for the single unsupported corner of the panel, where otherwise we would have, where you needed the sort of the plies to run both vertically and horizontally to that corner. So that's the sort of thing that the AFP provides for us. So this is shown in the costings. So the material reduction, as you can see there, the orange part of the bars is immense. It's a significant reduction, basically enabled by near net layup of the toe relative to sort of material nesting wastes that would have been there with a fabric layup. Price-wise, we're also using a lot more tow relative to fabric, which is obviously more significantly cheaper material format. Again, no honeycomb required, no adhesive, no inserts, etc., potting, adhesive, all of the other parts that are required for a structural interface to sandwich. So tooling setup comparable, and it's a significant move from 95% manual hours to 50% manual hours. So there's a lot less contact time. Weight-wise, we were able to undercut the baseline, not dramatically, but we have demonstrated the weight savings by weighing the two demo panels. So we have been able to show some weight efficiency. Next slide. This again, this sort of reduction in materials, etc., bears out or is borne out by work done in DLR by Jens Backman in terms of life cycle analysis with respect to particularly with CO2 emissions. So if you look at the chart on the left, or on the right, sorry, the sort of pink bar is the current baseline panel, and then the other two, the blue is the panel rendered using the SuCoHS process in the FST epoxy sort of baseline material we had, and then the green shows it with the PFA resin that we've been able to develop, as noted earlier by Deepa. So the key factors were, again, reducing the amount of carbon fiber used, as discussed before, and also the elimination of honeycomb core. I sort of quote Jens Backman there, but basically the honeycomb has a very large energy consumption for the amount of material you get. So eliminating it has considerably improved the sort of eco performance of the panel. Next slide. So again, our manufacturing development followed the same, or used the levels that the pyramid as discussed earlier, elements, risk mitigation, and final demo, as mentioned. Next slide. Key sort of detail points we looked at. The first one was to try and get a full fiber carry through at the crossovers by basically spreading the toes out alternatively per the diagram. It did result in a lot of gapping, so we did some work both at Coupon and during the RMS, looking at filling the zone with extra resin in the form of film. We were able to produce a structural carry through, but we felt it added a lot of complication and went against the drive to automate the process. So we took a pragmatic view of designing out the need for this sort of feature by virtue of sort of clever design of the stiffening grid or whatever. One good feature, one well sort of developed feature, was the ability to very accurately lay up a stiffener ramp. You can just about see the line of the ply ends set against just a 3D printed template we used as a check or a manual trim for some of them. So it does do a very accurate ramp down layup automatically. Next slide, please. Another key enabler for this was the use of a semi-stiffened bag to accurately mold the stiffener, the side, which would be on the bag side, and therefore an ordinary vacuum bag would not be appropriate. You know, Pavlos briefly touched on the comparison we did with like a machined metal set of tooling, but again, when scaled up, that would have been excessively heavy, complex, and expensive. So we were able to develop this approach using a master model, just an aluminium machined master model to mold the bag. It demonstrated on straight and slightly curved stiffeners. It did demonstrate very accurate or very consistent molding, slightly above nominal, but certainly very consistent within that bound, and also again consistent stringer height. The only point would be we need to make the bags more robust for any sort of production use. Next slide. So again, just going to go through the stages of layout now. The first ply down was initially the fabric, just to give a basic skin and surface for the overall panel. It also had the advantage of giving a good tacky surface for the machine and to lay up on top of. Then we had building up the UD reinforcements. So again, you can see the frame and the local reinforcements around the seatbelt pad up area. Next slide. Again, just a bit more detail. You can see the steered plies, how they sort of move over the pad up and move around the very tight radius at the bottom of the panel. Now, this is one, again, a learning point. We were sort of restricted by re-engineering an existing panel, which had the sort of the base flange and therefore a relatively tight radius for the machine to have to lay around. And I think if you're starting from scratch, you'll try and eliminate that sort of feature, or certainly massively increase that radius, or sort of work to engineer out the requirement for that sort of feature. And next slide, please. Just some more views of the stiffeners being laid down as the grid on the fabric. Next slide, please. Then the stiffeners fully laid up. So on the left, that's the sort of L sections of fabric being laid to reinforce the stiffener to skin joint. On the right then is just a trim template we used to trim off some of the stiffener ends that we hadn't programmed as a automatically laid ramp. It just was simpler for this to manually trim some of them. Next slide. And this is just going to be a video to just show the machine in action on some of the stiffeners if you want to go further.
I think we're a bit tight with time, Andy. That's okay if we go back.
No problem, yep. Go for it. Just the bag down and sort of sealed onto the tool. Next slide. Just this shows the final molded panel on the left and the trimmed panel on the right. And again, it's sort of fairly apparent if you look around the outside of the panel, just how near net we've been able to mold it relative to the trimmed final panel. So it sort of gives an indication of the material efficiency we've been able to achieve. So I think that's us.
Yeah. And thanks very much. Thanks very much to Nigel, Deepa, Pavlos, and Andy, and all the team that worked at this within Collins, but also obviously all the whole consortium that worked at this. I had another quick video here, but I don't think is necessary for the for this presentation. And again here, big thanks to coordinators first of all, but all the partners. Tobias, I don't know if you have any questions or what you want me to do. We are a bit late, I realize, but we didn't start exactly on time.
Yeah, thanks, Paolo, and Deepa, Andy, and Pavlos for your presentation as well. Really a lot of interesting developments, important developments and aspects you have been figured out. Again, due to the time issue, if you would agree that we collect the questions, and I think quite also some questions we might come back within our panel session when we look into feedback of the demonstrator and discuss also certification issues. Now, my proposal would be that we not only have 5 minutes break, that might be a little bit too short for you to have a bio break at some sort and come back relaxed and refreshed. So my proposal would be that we do have a 10-minute break now. What time is it? 26. Yeah. A 10-minute break would mean to start at 35 or even a little bit later. So yeah, let's start at 35 past. So have 5-minute switch here in our agenda. and then let's introduce the panel discussion for the next session here.
Okay, thank you very much then, and talk to you later.
Okay, thanks for all of you. Please stay online and talk to you soon.
So Tobias, you will start? Or...
So I think then I can give it a start. Just to briefly introduce, I must say this is kind of an experiment also for me personally, to have a panel discussion which is not live, not on stage, but via online, where we cannot really look into each other's faces. But at first, I can say I'm still very happy that we can do it in this manner. And I must say I'm also very delighted that you can take your time, especially also that, for instance, Simon Wade from EASA and Cindy Ashford from FAA made it possible to attend as well, to take your time and support us here in our questions and guide us maybe also a little bit further on. But the moderation of this panel discussion will be done by Professor Wiedemann, the head of our Institute of Composite Structures and Adaptive Systems here in Braunschweig of DLR. So at this point, we would like to really look into several aspects, and therefore, Professor Wiedemann, would you like to take over at this point?
Yeah, thank you very much, Tobias. So my name is Martin Wiedemann, and I'm glad to be the moderator of this panel session. It's also an experiment for me. And I welcome, first of all, Cindy Ashford and Simon Wade. Hello. Can you hear us?
Yeah, I'm here. Yeah, and you got Jeff Gardley in there as well.
Yeah. Thank you very much that you have taken the time to join us here, and also to be willing to answer some of the questions that the audience may raise in this panel session. First of all, to start, I would like to raise the question to our industrial partners from these three use cases that we have seen before. In a few sentences, what are your, let's say, next steps, and what do you believe that is still necessary? What actions do you take to go further regarding certification? Maybe Daniel, you can start. What are your plans to certify your EFS structure?
Okay, good afternoon, Martin. So I'll try and answer as best as possible. So in terms of the interfixed structure development, we still have some areas of development that we would need to continue with and want to continue with. I haven't really disclosed specific materials, but we definitely would like to further evaluate materials before concluding on what is the best approach going forward. So before we move forward and even think about certification, really, we need to bottom that one out. I think, well, I don't think, I know for a fact, of course, there's already applications in serial production out there in the world for this particular application, composite interfixed structure. So we know that automated fiber placement is a mature technology. This is a gap that we wish to close here in Spirit Aerosystems, and it's something that we need to delve into. Now, I would be particularly interested to know, I'm not a certification engineer. I don't have any much certification background, but I am keen to know, for example, and you don't have to answer this or anyone answer this now, but the certification authorities, how much do they rely on actual physical testing and exhausting the pyramid of test versus analytical process steps that we can reduce the amount of testing, reduce the cost, and also reduce the time required to do all of that. Now, this is probably a common question that everyone has within the consortium, so it doesn't need to be answered now. But
Yeah, thank you very much. So physical testing versus certification by analysis, I think that's a point we should discuss. So maybe Inigo, regarding the tail cone and the APU compartment, what are your next steps you plan to go for certification?
Yes, hello everybody. Yes, as it was said, we agree. I mean, what's the steps to be done in order to include some analytics in the certification process, and as I said in the presentation, mainly focused on the fire certification process, as I mentioned, because in the past we faced the certification, the fire certification campaigns without any prediction capabilities, and we would like to assist this process sometimes that are very I mean, there are a lot of uncertainties surrounding the fire response of the structures. We would like to in somehow to include some analytical tools to predict and maybe to assist the design of the certification fire test campaigns.
Okay, so fire certification process standards and analytical tools, that are the needs you address. Okay, thank you very much. And Paolo, maybe for Collins Aerospace, the question to you regarding your seed shell. What are the next steps you plan to go for certification?
We just completed recently the certification of the one you have seen at the beginning, one of the first slides. So for that certification, we had to qualify the material, and Deepa coordinated that work. And one of the key passages there is the definition of what is primary load path, and also if it is a single load path or a dual or redundant load path. So I don't want to go too much into the technicalities of these, but in a nutshell, I've been working at both in general aviation, in commercial aviation, and recently in interior. So you have a certain level of freedom of deregulation in general aviation, which allows you to be swift in developing new material, new technologies, which we know, for example, in gliders, in German gliders, we have seen composite for 40 years, and they've given us a lot of information on fatigue behavior of composites, as you know. And while when you are in commercial aviation, jetliners, so Bombardier, where I did work with Daniel, by the way, for more than 10 years, we have seen, obviously, A-bases, a very full, thorough certification process, and that is due because obviously that's a primary structure, is collective security for the whole aircraft, and also you develop a wing every 30 years. So some of the latest FAA TSO regulations seems to hint that we need to go for A bases for new material introductions. For example, we have been working with SAE on the ARP 6337, and we are quite happy with the definition of dual load path there, or the redundant load path. So I wouldn't mind a bit of clarification on what is our destiny or our future in terms of interiors and the introduction of new materials and this sort of area. Thanks, Martin.
Okay, yeah, thank you very much, Paolo. So that directly brings us now to the question of the certification. We have to differentiate between the primary structure and the interior, exactly as you said. And maybe we can address also the first question to Cindy from the FAA, because as I've learned, you are more focused also on the interior, and exactly the last question or the last point addressed by Paolo from Collins Aerospace is maybe something that you can answer there's this question regarding A and B values addressed. Do we need to go with the B values? Maybe you can give some answers to this question from Paulo.
Well, part of the question is what are you going to use the values for? When it comes to composites, we don't typically, especially in dynamic loading, we don't do a whole lot by analysis. You have to test, right? So there are some static test regulations, and even in that case, we have made the differentiation between primary and secondary structure. And oftentimes in secondary structure throughout the aircraft, if it's not carrying primary load paths, we haven't made the requirement to have a redundant load path in order to carry, in order to use B-basis values for control of the material. But those values really aren't being used in analysis. So
I can answer your question, Cindy, if you want. So what are we going to use those values for? And the question is, the answer is, so we're using it two ways. In the ARP 6337, the values are requested to assess your knockdown values due to material variability factor, and that affects, as you said, not the dynamic, but the static loads. So that's the first application. But the second one is the one that goes straight into material specification. So the values that we refer to during the qualification of the material are the values of the B basis or the A basis. My question is not just semantic for discussion, is that because your answer or the indications from certification authorities will drive the possibility of using new materials in live projects or not, because the qualification through A basis, and Deepa will keep me right here, requires a number of different batches and combination between fibers and resins that is not normally compatible with the live program. So that requires a very different approach. So that's quick answer, I suppose.
Maybe we just jumped in this certification issue without foundation. Some of you are experts, some maybe not that much experienced with certification. Maybe I can ask Simon to give us some introduction in this topic so that we can then go on in this discussion regarding details. Simon. Yeah, perfect. You've prepared something, I see. You must unmute yourself. Simon, your microphone is off. We can see your presentation, but we cannot hear you. Simon?
Simon, you have to unmute your microphone. We can see that your microphone is in red. It means that you have to unmute it. Otherwise, we cannot hear you.
So, yeah, perfect.
Yeah, if we
Great.
get that, it's obvious. It's shifting stuff around the damn screens, isn't it? That's the issue. But yeah. Right, what have you got? Yeah, so yeah, the 6337 discussion is interesting. It's only a first stepping stone. We didn't address bonding explicitly. There are a whole bunch of things that need to be moved on in that standard, but it started the process. And in terms of the A basis, B basis discussion, firstly we have to think about, there's the problem with identifying what is the primary load path. Until we're smarter with what we're doing in terms of understanding all the factors, whether it's environment, load, whatever it is. We want those margins in there because quite frankly, we aren't that clever with loads, certainly dynamic loads. So until we're cleverer with that analysis process or substantiated analysis process, I think we've got to learn to walk before we can run. So I would say A basis is the default for primary load path. And remember, a ship's set of seats, you know, if everyone fails on the day because everything lets go at the attachment or where, you know, local to the composite attachment area, and it kills a, you know, ship set of people, it's the same as a catastrophic loss. So that passenger safety versus airframe safety blurs. It's a big grey scale, but that's the principle until we learn more and understand more in test versus analysis. I think that's what you've got to start with. You can't run before you walk. So anyway, start with the basics. So yeah, so we've got Cindy here. We've also got Jeff online. Jeff, you are out there on line. Jeff Gardlin, who's a CS and TA cabin safety. So he'll chip in as well on this. So Jeff, are you out there?
Yes.
Yeah, good. Thanks.
Oh, perfect. Yeah, welcome, Jeff.
Yeah. Okay, great. Right. So I've got a presentation here, which is because it weren't clear which direction this discussion would go. It's a compilation of slides to help the discussion along. Because there's animations, I'm just going to hop to chosen slides as led by the people at your end in the team of interest to you. So I'm not going to run it in slide mode, so I have to work through all the animations. Okay, so just let me know if you can't see enough as it is. So I'll repeat that. I'm not running this in slide. I'm running this in conventional PowerPoint because I don't want to spend time on the animations. First point, just the basic apple pie stuff on the regulations. We have a set of high-level regulations which are binding, and we have the more guidance or soft regulation at the bottom. If you can see where I'm indicating the non-binding, that's the CSs and standards that we're largely talking about. But it's worth reminding people that the material and process part is embedded in the high-level legal requirement. Your materials and structures have got to be good for the life of the system, the airframe, the propulsion system, whatever it is, for the envelope and for the operational life. And that's all expressed and built into the type design, you know, material, methods, manufacturing, assembly, etc. And that's all heavily tied in with production. So design and production can't really be separated out. And we're seeing a lot of production design interface issues challenging us at the moment. So that needs to be tied together. So we go down from the base, those binding regulations to the guidance. It takes us through the basics. The 25 for large airframes, 603 materials, but very basic requirements, suitability, durability of your material must be based on experience and test and conform to specifications. For the certain sets of structure, you've got to conform to the 613, which is where it's more explicit about A and B basis. You need statistical credibility. And then we have the guidance material below that. And for composites, it's the harmonized AMC 2029, AC 2107B, which we'll refer to later. And again, please tell me which slides you want to see. I think these first two slides we're going to need to see for this discussion. So that's the loose framework, and that's just a reference to CS25, but the CS engine does pretty well the same thing, adapted for products. So and across the products, this is kind of universal structure.
So I'll take with me. Okay, maybe next slide. Yes.
Yeah.
Simon, continue. Yeah.
Yeah. Okay. So what's obvious about these clever materials that, well, okay, they're not so clever. Some of the composite materials have been going for a long time. You have these clever concepts to get around anisotropy material sensitivity going on. So when we start building our more complex parts, we've got to ask ourselves, where are the engineering properties in the test analysis pyramid? And the first thing you've got to think about is those engineering properties are a function of material and process, and the properties you need to know about may not even happen until you're high up the pyramid. So that's a really important thing. So although the base level pyramid work tells you something about likely failure modes for some forms of the material, it doesn't tell you a lot about necessarily about your high level design, and that's important to us. Now, we'll come back to this, if you're going to start optimizing your designs and claim you understand anisotropy fully, and then want to expect to go in the route of analysis, you're on a divergent path, and that's the problem we have to address, I believe. Let's add to that the environment that characterizes, for example, the qualification of your material, its reference points, the atmosphere, what's the temperature at altitude, what's the temperature on the ground on a hot day in the desert, have you got a big system working again next to your structure that modifies the temperature reference? That's all a function also of the configuration. So when we get to the flammability, not just the heat exposure in the terms of the daily certification environment, we've got to think, how does a fire work? That's a function of configuration. Is it external? Is it internal? Are we talking about an in-flight fire? Are we talking about a post-crash fire? So there's a bunch of things we need to think about around the pyramid. When it comes to high temperature materials, there are a number of activities. I know Cindy will talk to this at some point. We've in terms of engines, at the moment, engines in CMH17 world are focused on the CMC activities, SIC, OX stuff. You can start characterizing those, and but hey, they're working at a much bigger temperature. So you're also challenged by, how do we understand the use of existing methods, but in a high temperature environment? Is it actually physically possible to complete some of these tests? So we have to ask those questions about high temperature material qualification, and all of this plays through in terms of your threat assessment, in terms of the manufacturing threat assessment, in terms of what you get wrong in the process, through to the properties you get in the final build, the consolidated part, the cured part, whatever it is. That's defined, its damage tolerance is defined partly by the building blocks of material selection and understanding these failure modes. So I've just tried to really summarize there that your manufacturing and material selection for application is one of the threats in its own way, and the configuration is a threat.
Okay, thank you very much, first of all, for these explanations, Simon. I'll take with me regarding these question A versus B values. It doesn't matter if it's interior or if it's a structure part. A values are the state of the art, so we stick to the A values in these bottom part of the pyramid.
Yeah,
so that's the first point.
I wouldn't say that's necessarily a requirement. What you want is to prove that you're making something consistently, and you have different ways to do that, different ways available to you. If you're using it for an overload factor on a static test, you can determine that factor with tests at different scales. It doesn't have to be a coupon test. You can do it with some relevant subcomponents, and you will get much less variability because you're going to be driving failure into a more consistent location. I mean, unnotched properties are not useful for very much in composites. So if you have a more realistic configuration, you don't necessarily have to, you don't have to have that A basis overload factor.
Yeah, and Cindy's absolutely right. And I've got to add in there, one of the problems we've got here is we're talking about some product groups which have different needs. So we're going to have to keep in our mind which D4 you're assuming we're discussing here, because what Cindy said is absolutely right. But at the moment, I've got 6337 in my head. So it's all part of a grey scale, because it's about the proportion of the risk that comes out of it as you head towards hazard or catastrophic ship set loss. That's the bad end. And at the interiors end, you have some isolated applications where the risk is less of the occupants, if you see what I mean. It's a proportionality thing.
Okay, so we will take with us, Paolo, there's a certain room in which you can operate, not necessarily based on A and B values as such, but also on a higher level of testing.
Yeah.
Huh?
And that's part of the problem, is that once you get to those expensive, complex, higher test levels, you're not going to have anything statistically credible. So how do you deal with it?
Yeah. Maybe we can go also to the other colleagues who addressed this question regarding tests versus certification by analysis. And maybe we need also to before we answer or before we discuss this question, to have a little bit more a deeper look into the fire protection and fire protection certification issues and heat exposure question. Maybe Simon, you have also prepared some slides regarding fire protection, heat exposure.
Which slide do you want me to go to for that?
I guess it was a slide. What was it?
13.
What you've prepared? It's slide 13 starting, huh?
Yes.
Yeah, because we are, we're covering so much ground with products here as well. So is this the one you were thinking?
Yeah.
Okay, so this is just lifting a section from AMC 2029 on additional considerations. Fire protection, flammability, and thermal issues are highlighted. As already indicated, that's kind of broad. It includes the day-to-day normal certification envelope, but also the fire threat that comes from events, like a failed duct, anti-icing duct, or another fire source somewhere. So it's a pretty broad title. So I think we're all familiar with the idea of welfare thermosets. TG, thermoplastics, we can discuss what we really mean there. But we have a reference temperature, which may give you reversible, your properties a drop off after that point. It may be or may not be reversible depending on the material. The margin you have beyond that point is different material to material, and also different depending on whether it's wet or dry. And the means of determining the value, well, there are a number of options out there, but I think we're familiar with that. So the regulation, the important one for interiors people, is this AMC directs you away to the established interiors world, because there are a lot of the requirements for material for interiors have existed for a long time, and indeed we pull back some of the learning from that back into the airframe and other product application world. So you'll see a lot of repetition in AMC 2029, which is valid for interiors. So we say fire protection, flammability, thermal issues. Basically, we want to, we have to deal with the fire exposure temperatures, in terms of maximum operating conditions, and we might even have to require special conditions to explicitly identify those scenarios. And later on, we may get time to talk about, post-crash fire fuel tank, this kind of thing. So you've got to minimise the hazard to the occupants. It's fairly obvious. In the event of flammable materials, and considering fluids and vapours, and the basic threats that come out of the fire environment. And there may be, each class or each product class has some specific targeted considerations. You can show compliance by test or analysis supported by test, which is the universal regulatory expectation. You've got to remember that your design's got to account for repairs and alterations, and that means the repairs themselves and the interface or impact on baseline structure needs to be considered. And you shouldn't decrease the existing level of safety relative to metallic structure. And that's a real big challenge, how you define the existing level of safety.
Simon, there's one interesting sentence in the middle of this slide. It's compliance may be shown by tests or analysis supported by tests. And as far as I understood our industrial colleagues, this is exactly the question
absolutely.
to answer. How much support by test is required,
Right.
suppose you have a very perfect analysis.
Yes. Well, back to the test versus analysis or test analysis pyramid. Right at the bottom, you have a statistical link on what you're doing. If you go laminar to laminate, you can kind of use failure criteria to predict something about the scatter at a laminate level from a laminar. Above that is an engineering judgment about what you include in your test analysis pyramid. The numbers of tests against complexity, criticality has been a long established case by case built up database experience supported by analysis increasingly. Some manufacturers have in-house established small data set management philosophies and practices. But that is not standardized, and it's a subject which is, as you're probably aware and we'll talk about later, it's a really big subject, and this matters for all of these integrated technologies. We're getting sucked into the world of Bayesian statistics and what that means, and how do you show equivalence using your Bayesian stats to the existing level of safety? Where's the benefit from using that approach? So all of this comes into play here. So the empirical aspect is really important. And back to the anisotropy discussion, we have a very limited number of tests, dynamic tests for seats, the classic seats with metals. Having an isotropic set of material properties cheats a lot of uncertainty to some extent in the loads detail analysis. Once you start tuning for your anisotropy, you're kind of losing that. So the point is, if you start tuning your design, it says to me you really should be doing more load cases at the top of the pyramid to offset the potential for those uncertainties, or you should have more load points around the envelope but at a different point in the pyramid. So I'm just throwing that in as a thought at this point, but that's the problem I mentioned earlier. We have a divergence, and can we keep the two together? Can we keep our substantiated analytical capability close enough to the divergence in applications and optimized design?
May I ask the colleagues here, Daniel from Spirit or Inigo from Nova, taking this answer from Simon, what are your questions or concerns? I mean, you raised the question also regarding tests and the need of supportive analysis. Now you have the chance to ask Simon directly, what do you need to do to get your parts certified?
Yeah.
Yeah, I'm trying to think on the spot here, Martin, what I need to ask Simon. But I suppose, Simon, that thinking ahead, for example, the fiber placement process itself on such a complicated double curvature structure will, depending on what way it's the programming is assigned for each layer, you will end up with sectorization required. And you will end up with voids and gaps, and depending on your philosophy, you might have gaps or overlaps, etc. But it springs to mind with us, and particularly in Belfast, that we have limited knowledge in terms of certification of fiber placement products. How exhaustive does the test, not even the test pyramid, but even at coupon level, for example, how exhaustive does the testing need to be in terms of substantiating some of these required features?
Yeah, well, let's start again. If we go back up the pyramid, we're moving to performance-based regulation, which is criticality, novelty, and complexity driven. I would start with what's your hazard analysis or your FMICA look like? Let's start with that. That will bound what your first step is. If you can consider every possibility of how that might fail or how that failure might change relative to your conventional way of approaching the design, that's a good start. Then you can start to frame the discussion. You can put in some mitigations. I mean, we know that the quality of some more conventional materials is improving. You know, that's reducing your scatter. But if you're going to start optimizing that design, then you've got to allow for that. You've got other failure modes coming in, and that's where you've got to use your hazard analysis of a maker. Again, you can take different ways of looking at this. If you use that as your bounding tool and you can really use it properly, that gets the criticality in place. Then we can start talking about what you might need to do in terms of number of tests. But as I just said, at this level of structure, you're not, you know, there's statistical credibility is challenging. And if we're talking about sandwich structure, that adds another dimension into the process. And also, you've just touched on another really important point, which is, I've already mentioned the design production interface, which is actually supply chain interface. And as you know, there is also a need for a clear communication right through the chain about how what the failure criteria are, what the guidance is. And it needs to work all the way through the process. So the type cert holder as a systems that, you know, as being involved with a propulsion structure on a propulsion unit that's attached to a type cert holder's airframe, whatever you're doing should be consistent with the aircraft level safety right at the top. That's the important thing. And that should be coordinated through the chain. And that's
in general,
yeah.
I mean, I guess, you know, they asked what do they have to do because they don't have experience with the fiber placement.
Yeah.
I mean, the requirements are the same, whether it's hand layup, whether it's resin infused, whether it's automated fiber placement. So I mean, that doesn't change. Now, if you have now specifically for coupons, if you have a material database based on hand layup, and you're now taking that same material and doing it fiber placement, you can use equivalence testing to buy into those same material properties. Unless you want to take credit for something better, then you do have to create a new database accordingly. But I mean, those concepts are really unchanged just because you went to, you know, tape laying, automated tape laying.
Yeah, that's good, Cindy. You brought that in nicely. I mean, the shared database thing is important, and yes, the move to performance-based regulation is generalizing this. It is back to if you read 603, 25603, or the engine equivalent, it's that basic. I mean, it really is.
So, but what you're saying, Cindy and Simon, is there's no difference between, let's say, normal static sizing values, evaluation, and these fire and heat exposure issues. So regarding the material properties or regarding the production technologies used to produce the parts, there's no special requirement regarding fire protection and heat exposure.
Oh, there is. I mean, there's a whole raft of fire protection test methods which we reach to in the interiors world, and in the propulsion structures world, which we pull forward into the more extensive use of composites. So, I mean, you know, again, Jeff might want to say something about test methods and how he's dealing with those.
Yes, but regarding the production technologies, there's the same, let's say, same way to follow.
Yeah, you've got to. Yes, you've got to deal with the variability. I mean, from the additive manufacturing point of view, they were spending a lot of time on this discussion. You know, how how much testing, how much sensitivity do you have? What are the key parameters? Does this fundamentally change your burn? You know, the burn properties you're getting. So it's right to the manufacturing threat assessment level. That's all part. But it's the same rules you're meeting.
Yeah, material and process control methods are generally unchanged. Now, when you have the fiber placement, of course, you have you know, some options for perhaps in situ, inspection and how to react to that. But whether you're making primary structure or secondary structure or high temperature applications, these concepts are unchanged because of the fact that you've added temperature. you will have to characterize your materials, obviously, for the operating temperature that they'll be exposed to.
Yeah.
But yeah, Jeff would know if we have, I mean, the question of can we use analysis for fire regulations, be it interior flammability or fireproof, fire resistance as required. I don't think we do. Jeff, you want to elaborate on that?
Yeah, well, I mean, I'll say a couple things. So far, there is no analytical substitute for the flammability and fire tests themselves. We have used, and we do use, comparative sorts of analysis to determine what it is you have to test. So if you look at the envelope of design variation, there are ways to determine within that envelope, which configurations are the critical ones for test. And that's relatively common, and we're still learning on that too as to what's important. And it varies depending on what it is you're looking at. So, most of these tests for the materials, particularly with the interiors, the main purpose of the tests is to evaluate whether these materials contribute to the fire. So you're not really asking them to perform any particular function. You're really just trying to measure their contribution and minimize that to the extent possible. Let's see. And the other thing I was going to say is, and Simon was alluding to this, that the idea is that you're testing the design and you're testing the critical configuration of the design. But where it starts to get a little bit interesting nowadays is, what is the design? What are the factors that go into making up the design? And if you consider the process variations, where the main objective is to arrive at a structure that's capable of doing certain things, some of the variation in the processing that is shown to satisfy the structural requirements may be critically important in the flammability performance. But depending upon how that's been defined in the test plans and so on, it's potentially overlooked, or could certain things could be overlooked because they've been established as equivalent from a structural standpoint. They may not be equivalent from a fire performance standpoint. And so again, we're trying to identify what those things are and make sure that when we do allow some analytical reduction in the test spectrum, that we're doing it based on actual data and knowledge and still testing what's critical.
Yeah, Jeff, that's a good point. Yeah, it is. Yeah, classic engineering, isn't it? If you start to gain somewhere, you lose somewhere else, and you've got to know that's happening.
But now, looking to this SuCoHS project, and you have listened to the outcome of the various use cases and the studies performed. What are your impressions regarding these results? Would you say, or turn the question the other way around, what are still missing points or major gaps you would suggest that we have to consider in the next step or next research projects of this type? What would you wish?
In the very short period of time that we've got and the breadth of what we're trying to cover, it would be difficult to say. But I mean, to my mind, it's looking at the threat assessment. It's going for understanding the end-to-end situation. And as Jeff was pointing out, you've got to think about, if I'm working on this, how is it impacting something else in my chain? In terms of the product, how it behaves. Is my get into the hazard analysis assessment and a thorough hazard analysis assessment on what it is you think you're doing, and you can't do it in isolation. It needs to be from the material supplier, the types that hold it down to the material supplier, and you've got to think about all the possibilities. That's all I can say. I mean, damage tolerance is the key in my mind. From a structures point of view, everything hinges on that. So that's where I look. But with my airframe bias.
Okay. So one big message is the suppliers have to be taken on board. It is not sufficient to prove sustainability or fire proof of materials without a complete supply chain behind. Huh?
It's a good idea. I mean, you can test your way there on your own, but you need to have enough communication down the chain to understand when something's being changed, because part of your certification is about having a structure in place that ensures you maintain those design values throughout the production cycle. And as simple as it sounds, there's quite a few problems out there that have come out of not paying attention to that, and something minor within the scope of a perceived type cert holder specification gets translated in a reasonable way by a production organization, who then translates it in a reasonable way in terms of their supplier, and you end up with your design values being changed and you didn't realize that.
Yeah, understood. Now a question to our industrial colleagues here. Listening to the answers from our colleagues from the authorities, what are your ideas or expectations regarding next steps in research? Do you plan to perform more research on the analytical methods, or do you think you have to perform more tests, or what are your needs for further investigations?
Yeah, regarding. Sorry.
Yeah, continue.
Sorry for that. Okay, regarding Arnova, yes, I mean, we plan to keep unfocused on the fireproof, on complying with the fireproof requirement and fire resistant requirement. I mean, we have started to understand what are the response of the composites against these fire events, and we've tried to put that understanding into the tools in order to have some prediction capability. But for sure, we know that we are very far from an accurate understanding and accurate simulation or prediction of what's happened. But okay, it's a step that we've have already started in SuCoHS, and we would like to go on in order to for sure not to remove the fire test, the certification fire test. For sure that we are very far from that. But okay, as it was mentioned, maybe to try to have better or to have some tools to make better designs, and maybe to have some capability to understand and to choose between several options which could be the best one, and maybe also to work in the test development campaigns by by having the capability of selecting also the development test in order to rescue and to have appropriate data to understand what is gonna happen in the final design. And so I mean, we know that are very far, but we would like to keep understanding the problem, to keep to passing all our understanding to the simulation tools, to improve numerical models in order to have this assistant capability for future developments and future fire certification campaigns.
Yeah, thank you very much. Inigo, there was also one question during your presentation. It was related to the 5 versus the 15 minutes proof, because the fire protection is 15, the flammability, as far as I've understood, is 5 minutes. You mentioned only the 5 minutes. Have you made the test also for 15 minutes? So
Yeah, I mean, it's one of it's the what is required from the regulation. I mean, it's that it's the aircraft on ground. You have a fire on the APU, and the crew knows that the fire is taking place in the APU, and just turn off the motor. That's because all the load requirements for this particular case on ground, which we consider that is the most critical one for that. Panel, that tailcom panel, is just 5 minutes loading and yes, and 15 minutes fire.
Okay, so understood. Cindy, you just made a proposal in the chat. Maybe you can explain it or say some more about it.
Well, there were 2 things. You know, you had asked what the regulatory thoughts were on future research. And one that I think often lacks in research documentation is the limits of what you've done. What design constraints did you employ? What are the limits of the analysis? If you have this thermal analysis of behavior, what is it applicable to? You know, is it, you know, how many plies, you know, a low end and high end, or does it have any orientation limitations, which I wouldn't think, but whatever. You know, these types of things, you know, I'd really like to see documented in your results. In general, when we allow analysis, we allow interpolation, but extrapolation is, you know, not something that we generally do. The other thing I suggested, you know, if you're going to be getting into structure that's exposed to higher temperatures or low temperatures, you know, it happens that way too, you're going to have thermal loads in opposite directions at any metallic interface, right? Because one's not expanding and contracting and the other is. And this type of load cannot be applied at full scale structure. It can be applied in coupons.
Yes.
And so that's a real use of analysis is substantiating those hybrid thermal loads. The only way to do it is by analysis, but it has to be based on some type of subcomponent testing.
Yeah, fully understood. Yeah, there's clearly an advantage of analysis because you cannot perform those kind of tests on a real structure. Yes, I fully agree. But coming back to this question, or I reformulate the question. If we look to fire protection, heat exposure, flammability of materials, do we have, I mean, we have these 5 and these 15-minute flame exposure with this energy amount and heat temperature, but is that sufficient as standard tests for all the materials we are and all the applications we are looking for? Do we have sufficient standards for testing of materials regarding fire protection, flammability, and thermal issues? Is that satisfying what we have?
That's an interesting question because it depends on the product, but it's an iterative question, as I think you can see from the evolving crews and the CERT memo, because in the end, the key is the criticality and exposure. Is it going below the load limit? Is your system functionality compromised in those time zones? If you've got whatever material it is and it can protect you from the consequences, then that is what we should be thinking about in the future. At the moment, we got too hooked on the classical reference points of certain metals of certain thickness. Okay, if you want to design around that, that's fine, but that's not the only option. That's my take on take on it, sir.
I just see Jeff has also here give a message, and you just put a link here into the chat. Do you want to say something to this link?
Yeah, I can. I mean, a few years ago, the FAA developed a research test methodology called microscale combustion calorimetry, or MCC, and we've been trying to further develop that method and find applications for it and so on. And one of the things that has recently kind of evolved is the development of a way to kind of characterize with a physical or find a physical basis, I guess, for certain combustion parameters. And so that report kind of discusses the evolution of that and this characteristic that they defined called the fire growth capacity. But it has some potential application, you know, in an analytical way. It's not a substitute for the tests that are required, but it is potentially a way to identify early on things that are likely to be acceptable and things that aren't.
Perfect. Yeah, thank you very much for this advice, and the colleagues will copy this link into their folders. Regarding the boards, I mean, there are these certification rules under development always, and there are, I guess, there are some boards where the OEMs and the authorities are working together. Are there also suppliers involved, or what is the forum in which certification rules and their application, the acceptable means of compliance are discussed regarding these fire protection flammability issues?
If I understand the question correctly, it is back to earlier, as Cindy said as well. The rules are still the same rules. The supply chain issue is something we want to improve. We realise, for example, that the interface between the TCH and the type cert holder and the ETSO or TSO, there are issues there that need to be tidied up. And the supply chain needs to realise it needs to share what it needs to share to achieve the objectives that Cindy was talking about. Yeah, and we have this problem that carryover of damage tolerance for composites into composite seats is a problem for some organisations. The information transfer from the ETSO, it's a problem.
Okay, but the regulations stay as such until, let's say, an OEM is coming and propose something better. Am I right?
It doesn't have to be, but usually the larger OEMs are in a better position in terms of test capability, database development. They're usually the ones with a history.
Okay. Yeah.
I mean, in general, we work with applicants and pre-applicants through industry organizations, you know, conferences and whatnot. That's where we tend to interface directly with suppliers without having, you know, the airframe manufacturers or engine manufacturers.
Yeah, good point.
Also in the room. And then, of course, if someone is suppliers can get TSOs, such as for an APU.
Okay.
And they can do that on their own without, I mean, then they become a design holder. It's just not, you know, a product design.
And that's a good point. Like CMH17 is a good exercise in joining up all the stakeholders to try and kind of bridge some of this gap. So.
Okay, very good information. It is new for me. Yeah, okay. Thank you very much. Coming to a last question. I mean, the forum, I just took some questions from my notes, but maybe there are some questions from the forum. I have not yet seen some more. Tobias, have you had a look into the chat?
Yes, there have not been additional questions in this chat.
So I have now the chance to raise my last question. It's regarding sustainability. I mean, we are facing now a growing challenge to introduce materials, biomaterials, as it has been mentioned also by our ANOVA colleagues, into our products, into the application for the aircraft structures. Do you believe that there's, from the authority side, something special to be considered regarding biomaterials? I fear yes, because they deviate in their properties much larger than chemical materials or metals. Do you believe that biomaterials can be a significant part in future?
Again, it is, you know, it's still going to need to meet the same rules. And if you design and you can deal with the bigger scatter, as long as, let's say, for example, as regulators, we like to understand what the driving failure mode is or damage mode. You know, if you've got a whole load of competing failure modes and a massive scatter, we're kind of concerned. But if you've got something where your design allows you to account for that scatter and it's a dominant failure mode, you're somewhere else. So in terms of the design, but the basic rules are going to be the same. And you may have to introduce, you know, your environmental consideration may involve you to, you know, maybe you're more sensitive to degradation of, you know, when exposed to certain chemicals or whatever it is. There are going to be other criteria, but the requirement is at such a high level in that statement, particularly for damage tolerance. If you're going to go that reference route, that, you know, you're in the same place. It just drives you down the detail path in the problem area or the challenge area you have.
Yeah, okay, quite reasonable. Something to add from our colleagues from FAA? Is this a discussion that you are facing with your customers also, biomaterials and their use? Okay, no. There's one question in the chat from Paolo.
Yes. I think it can be, again, a loop back maybe from the biomaterials, which have maybe a higher scatter, back to the scatter when changing the manufacturability and repeatability. Paolo, maybe you could directly rephrase.
Tobias, I know we are on the same page on this, because on the previous program, on the ECOMISE program, we did work a lot on robotic repeatability versus what is the scatter. We know when we have the classic manual honeycomb constructions, we have the scatter, and there is the, you know, manual layup doesn't really, is not really associated with repeatability. So in the general aviation world, we used to have factor of 1.15 due to this variability we had to account for whenever we use hand layup. Or in this, you know, in this world here, or primary structure, commercial structures, we have, for example, knockdown due to the whenever you use, when you work with metal, you use casting, you have an extra value. So in this case, I can see where is the advantage from a regulatory point of view when we work with robotic layup. So when we ensure consistency against a type of composite manufacturing that has a larger scatter.
That comes back to the equivalence, or the artificial intelligence, machine learning, digital twins, all of these things. It's how do you show that you've not reduced the existing level of safety, and that brings you into extra layers of statistical consideration. And have you identified the key parameters? Are they weighted in your statistical model appropriately? It becomes all of these discussions, and that's why there is going to be this need to deal with what equivalence means in a complex structure. Relative for safety, I can't, you know. So the fact is, casting is, you know, additive manufacturing. We've had that discussion. No, it's just castings. Well, no, it's not. You need to, by the time you've proved that your population is part of a casting set to attract the factor that you have, you may as well have just done the full A/B basis or whatever it is. So, and you're going to be inspecting anything critical 100% anyway until you justify a sampling step down in production. So, yeah.
Yeah, but the A-base and B-basis, Simon, is normally calculated at a coupon level. So at coupon level, it's not easy to capture variability at the coupon level. You normally capture variability.
Yes, I know, and that's what I'm. That's what
you can tape lay coupons. That's what people do, right?
Yeah.
Oh,
you
yes.
extend your tool and you place a panel.
Sure, you can do that, Cindy. But the problem is at coupon level, you don't see the variability of your hand layup.
No, you can create a database with coupons made with tape laying.
Yes.
All right, and if you don't want to do that, then if you want to take a database that already exists for hand layup, then you can buy into that database with equivalence testing.
The complexity of hand layup is whenever you have to laminate complex parts, and that's where we receive all the time parts that are not exactly as we designed them. So we need to.
That's the building block.
That's the problem.
That's why you go through each step of the building block to validate.
There is no
I think that's
statistical.
to be captured.
There's no statistical standard for that higher up the pyramid.
And there's no, there's no physical modeling that will, let you take a coupon lamina property and truly predict full-scale structural behavior. You can't do it. The math doesn't work.
Doesn't work.
Everything will be full of fudge factors all the way up as you add more and more complexity.
Yep.
So how do you do it? It's up to the applicant to decide how to do it. There's no standard methods.
So we'll come up with proposals and see if you like them.
Pretty much, unfortunately. But as soon as someone wants to create but the problem is, people create a method to do this and they don't want to document it. They treat it as intellectual property. So I can't tell you how to do it. I can't say, well, company A did this and company B did this, unless someone decides they want to publish best practices and share it with everybody else.
Yeah, and that shared database example is, the German, the AFF, HFF group. They're kind of not just base of the pyramid, they're sharing higher pyramid activities, bonded joints, this kind of thing. So that's an example of a shared database, which was a closed shared database. And there is the working group aircraft certification, which is trying to expand that for GA and rotorcraft, so that you get those commonalities. And that Cindy has been behind trying to move TSOs up to a shared database discussion or a shared model use discussion. Which I think might have value where the commonalities exist.
Okay, thank you very much. Looking to the time, I fear we are now over with our discussion time. So I would like to thank all the discussion partners, our colleagues from the industry, and especially our colleagues from the authorities for this discussion. And I would like now to hand over again to Tobias. If there are some remaining questions, please feel free to put them in the chat. We will try to answer them or to help answering them in the, later on. But now, Tobias, I think you have to wrap up.
Yes, thanks. Also from my side, all of you taking part of the experiment here to have this online panel discussion. And thanks again very much for your patience also in being available for us, sharing your thoughts, sharing your questions. And I guess we can stay in touch here, even if further questions will arise after that meeting, that we can share information. By the way, I would like to ask also you, Simon, if the slides that you have partially shown, if those can be distributed even after the conference, if you could agree.
Yeah, you can share all the whole pack of slides there, and I think Cindy might have something she wants to put in there as well that's useful.
Okay, yeah, thank you very much, all of you. It has been a pleasure, really. And now I would like to wrap up a bit. I don't want to repeat everything what is said already. Yet you can see that we have looked into the overall demonstrators, and We have talked in our panel discussion about what have been the challenges, and we have seen there are quite a few issues, and sometimes the answers are possibly easy and possibly difficult in both ends, and basically main engineering and concise work. But we have to be careful, and there are also research activities that can be derived from it. All the videos and presentations will be shared on our homepage afterwards, so for everyone to be downloaded. As a wrap-up, I would also like to outline the day of tomorrow's day. Increase so that you can read. I hope it's readable for you. Sorry. Sorry, it's time lag here. So I hope the agenda stays. Can you read the agenda?
Yes, it's okay. It's okay, Tobias.
Just like this. So thanks. So we will have a continuation tomorrow with further details on the individual technologies. Today it was more or less the overall stories that we have discussed, and I think there is more room tomorrow to dig into details. The particular presentations will be very short in this case, so we only have 15 minutes slots, which is rather short for conventional presentations. And but the idea is that we do have these presentations in a row of 3 or 4 presentations, depending on the session, and then start to have a discussion afterwards, let's say after the material session, after the session about industrialization, for instance, so that we can have also again here an overall discussion about the topic itself. And if you need, again, further time for that, you might be invited to use the lunch break, for instance, which is shortly after 12. In parallel to the lunch break, just 15 minutes later starting, so giving you the chance for a small break to have a coffee or the opposite. And then at 12:30, we are also proposing to attend a virtual lab tour. This is also an experiment, I must say, since you are not here neither at NLR's place or Bombardier's or Arnova's or DLR's place, for instance. We have thought about how can we do it. So people have prepared a live demonstration of, in this case, of a thermomechanical test, how the environment works. And so maybe it might be interesting for you also to attend this one. So here, this will be done in 2 slots. On one hand, at 12:30, on the other hand, at 3:15 in the afternoon. It will be both exactly identically the same. So that gives you the freedom to choose which slot suits you better in case you have other appointments as well to take. So this is what I'd like to wrap up at this point. And I hope this first day was interesting for you as well. I was quite excited, I must say, and I'm also looking forward to further discussions after that day in the next weeks. So I'm not sure if there is still a question, then there's time for it also. If you have a question to raise, maybe we can answer. All right. If there comes something into your mind, also don't hesitate to just send an email and then we will come back. So thank you all for this first day. And then I wish you a nice evening, or for those of you in the States, have a nice day still up front. And then we can see each other tomorrow. Thank you very much.